Welcome to this 3D rendering and scene assembly series. In the series, we're going to be looking at how to use USD, which is a framework developed by Pixar for scene assembly, and we're going to be using Houdini and Solaris inside of Houdini to actually work with that framework. So what is it exactly, and why is it relevant to you? Okay, so my brother and I actually taught a workshop in London to a bunch of 3D artists from different backgrounds, and some of them were lighting artists, some of them were compositors, some of them were TDs, and we kind of just showed them how to use Solaris and USD. And this is relevant because a lot of software packages are picking up USD, they're also picking up MaterialX, which is something else we cover in the series, and they are now allowing USD-based workflows. This is also important because that means that a lot of studios are now getting quite interested in how USD works and how they can implement it in their pipelines. So whether you're a Houdini artist, a Maya artist, a Blender artist, it doesn't really matter. In this tutorial series, I'm going to be explaining how to use USD, but we're also going to be using Solaris. So Solaris is just Houdini's toolset for working with USD. And USD is a way for us to build our 3D scenes. So USD is a scene assembly framework. Solaris is the toolset to use that framework. And so we are going to be using Houdini for this tutorial series, but you don't need any previous experience using Houdini. I'm going to be showing you like the absolute basics of navigation in Houdini. You can skip that part if you really want to, but you don't have to be intimidated by the Houdini aspect of it, because really I'm not going to be doing anything that's particularly Houdini specific. It's all about Solaris and using USD. So how exactly is this series going to go? Well, I'm going to start with the basics. But what I'm going to be doing is opening up some files that I have included down below for download. It's a bunch of assets and textures, materials, all sorts of things. There's a bunch of pre-made Houdini files. They're all annotated. You can open them up. I have them all there for your reference so that you can always go back to them and kind of see how different setups are built. The idea is I'm going to be going through each and every one of those files, explaining the core concepts that make it up, and sort of rebuilding those files in a lot of cases, so that you can get a deep understanding of how each and every concept works. So let's get straight into this tutorial series. We're going to begin with part 1. Alright, so if you haven't opened Houdini before, this over here may seem a bit intimidating, but I'll try to break it down in easily understandable 3D terms that are applicable through most 3D applications. To start with, we have our viewport. Now, this viewport is where you're going to be placing objects. You're going to be doing your scene assembly in here, and that's going to be important as we move along. But basically, any geometry goes in here, your lights, your cameras, and as you can see in the bottom left, it also shows us our axes. So we have X, Y, and Z, where X is horizontal, Y is vertical, and Z is your depth. So to move around in the scene, we can left click to tumble, we can middle mouse click to pan, and then we can right mouse click to dolly, or alternatively just use the middle mouse scroll wheel, right? So scrolling in and out. So just to do that again, left click to tumble, middle mouse to pan, and then right click or scroll wheel to dolly in and out. All right, so this is just a basic viewport, but oftentimes we will need certain display options and things like that. All of those things can be found on the right. So those are all of your visualizers and display options for adjusting how your viewport appears inside of Houdini. So you can do things like hide this grid, right? So the reference grid, you can hide that. You can change the type of lighting that appears in your viewport. I'll show you that a bit later. And if you want extended display options, you press D while hovering in your viewport, and it brings up this entire set of options, right? So you can do things like change the background to a dark color. All of that is inside of here. So remember that. Just press D when hovering in your viewport. That'll just bring up an extended version of what's on the right-hand side. That just brings us onto what's on the left-hand side. By default, you'll be in this camera view mode, and that just allows you to navigate and move around. If you're in a different mode, like the select mode, you will no longer be able to do that, right? So this is for selecting objects, your geometry, and then you can move things around and scale them. You have all of these transform options over here, but all of these are kind of combined into a single tool, which is your transform handles. And when I place a piece of geometry, you'll see that you can just use the transform handles to move things around. If you want to temporarily return to your navigation set, so return to this view mode over here, you can obviously click there, or you can just press spacebar. By holding spacebar, it toggles the view mode back on. So even if you were in your transform handles, you can press spacebar and then you can move around. Alternatively, you can press escape, and that just returns you to the view mode. All right, so that's just our viewport, right? So basic navigation, that's going to be important for us, especially considering that we're working with scene assembly. The next thing that we want to look at is this on the right-hand side. Bottom right, we have this object network. Inside of Houdini, this is where each and every object that we place is going to go. Let's just place an object so that you can understand exactly what's happening over here. So if we press tab, that brings up our tab menu. Again, we're going to be using this a lot. So remember, tab is just a hotkey to bring up your tab menu that allows you to type in whatever you want, right? So if we type something in here, like a cube or a box, we'll place a box, press enter, it allows us to place a node, and then we place this node right over here. So that's one object in our scene. We can now navigate around it, and you can see that this yellow outline just tells us what we have selected in our scene. We don't have anything else to select, but if we click away from the box, then you can see that it deselects it, right? Or alternatively, you can select it like that. So that's just showing what we have selected. Now we can place other things in our scene, for example, cameras and lights. So don't worry about where those are being placed right now. Just understand that all of those are considered objects, right? So this is where you would usually do your scene assembly. So I'm going to switch back to my view mode, but by default right now, it is locked to whichever camera or light I have selected. So if I move in my viewport, it will move where that light is positioned, but I don't necessarily want that. So I'll switch off the lock and I can just now move around as I've done before. So as I mentioned, these three are objects, right? And each one of these actually has a set of parameters which we can control. For example, this box over here, it just has some transformation options in the top right. And the top right is our parameter window. So this is where all of your parameters exist for whatever you have selected in the bottom. Each one of these are nodes. So if I select this node, these are the parameters for that node. You can see that it's this geometry node called box 1. If I select my camera, you can see that my camera gets highlighted, but I also get some options for my camera. Things like its transformations, as well as all of these things over here for its aperture, focal length, all of that. Additionally, I also have this point light. And this point light, once again, it has options or parameters that are specific to the point light. Okay, so if we wanted to say render this, right? What would we do from here? Well, this is our object network. If we take a look in the bottom right, you can see how it says OBJ. In the top right, it says objects. Now that just means that we're within the object network. Now, something to understand about Houdini is that it has different networks within it. You can think of it almost like rooms in a house, where Houdini is the entire house, right? But you do different things in different rooms in the house. There's a bathroom and a kitchen and a bedroom, and each one of them has a different function. That's how I like to think about Houdini, where they're all interconnected, but they each have their own set of functions. For example, the object network is where you place your objects. But if we were to go to something like the material network, you could place materials here, like a principled shader, right? And you could build a material over here, and then you could go back to the object network. So again, click on the dropdown, go to the object network, and over here you could, assign that material. So onto this box, we can go ahead, and in the material network, we have a principled shader that can be assigned to this box. So just like that, if we now go to the material network and we make changes to this material, you can see that it affects our box, right? So this is a separate network from the object network, but they still communicate between each other as if they were all part of the same system. This is the same thing when we want to render this out. If we were to render this out, we would go to the out network, right? From the out network, you would drop something like a mantra node. This is the old way of doing it. I'll show you how it is currently done in Houdini, but if you were to render with mantra, this is how you would do it, right? You'd have all of your things over here, and then you just go ahead and say render to disk. That'll render an image using mantra. And again, all of these things are interconnected, but they all exist in different networks. Now, that also means that we can create instances of networks. And what that means is that I can create a material network at the object level, right? So this material network over here exists independent of that one over there. It's an instance of it. So I can dive inside and I can create materials in here, like another principled shader, and I can make a bunch of changes over here. So let's make this one this green color. And now with this box geometry, I can actually, instead of going to the material network over there, inside of my object network, I now have a material network. So we're kind of understanding this idea of hierarchies, but we basically just have networks, and networks can exist within each other. So just like this, I have an object network. Inside of the object network, there's a material network, and inside of there is a principled shader that I can apply to my cube. The only other thing that I really want to bring up is that this over here, this box, this is a container for the geometry that lives within it. So if I open this up, I actually have a box over here, and this is a different node, right? This one over here is just a container. This one over here is the actual box geometry. So I can make changes to this box, like rotations, like that, and increase in its scale like that. One thing to note is that I incrementally increase the rotation by middle mouse clicking over here and just moving back and forth on this parameter. You can also move up and down to increase or decrease the increment amount. And so you can move it like that, right? So for finer control, you move down, and for greater control, you move up. Okay, so we just have that, right? And from here, you can do all sorts of things. Like I could subdivide this box if I drop a subdivide node, and you'll notice that I have this blue flag on the edge of my node. That just means that this node is what is being displayed, right? So if I switch my display flag to something else, the subdivide, it will then show this node, right? So this box is one node, the subdivide is another node, but it's taking the input of the box and it's applying changes to the box. I can increase the subdivisions just like that, and my cube just gets subdivided into a ball. Okay, so if I go up a level, you'll see that I now have the sphere, because inside of here, my display flag is set on the subdivide. I can change it back, go up a level, and it's back to what I started with. The only thing that I didn't really look at right now is the top over here, where we have our shelf tools and the timeline at the bottom. Shelf tools are just presets. You can place all sorts of things. For example, instead of tabbing in a camera like you do over here, you can just place one from the shelf tools up there. Same thing with the point lights and so on. You also have some presets for simulations. For example, there's a viscous fluids tab, and you can do things like melting objects and that. Your shelf tools are just sets of presets or nodes that you can drop directly. All right, and by clicking and dragging on these thin bars between different panels, you can resize different windows and things like that. You can increase particular window sizes, and you can also minimize them. So if I click on the arrow over there, it either expands it or closes it. So those are just a few things for navigation. If you find that your navigation is kind of broken, so let's just say that I've somehow managed to close my scene view and I've minimized that window and I don't really know how to get back from here, all I have to do is go up to this build over here at the top. These are our desktops, and all I have to do is just say reload current desktop. That will just reset us right back to what we started with. All right, so now that we understand navigation, we can go ahead and move on to actually working inside of Houdini with all of the stuff that we're going to be learning in this series. So let's get straight into that. All right, so hopefully you now have an understanding of the basics of navigation inside of Houdini. So we can start looking at some key concepts that we need to understand. So let's first look at scene descriptions, USD, and how they all work, right? Why is this important? So firstly, we have to understand what a scene description is. When we are putting together a 3D scene in whatever software package, right? It doesn't really matter. It could be Houdini, Maya, Blender, whatever software package you use to put together scenes, this still applies. When we are putting together a scene, that is called scene assembly. This is where we bring in our geometry and our lights and our cameras, we add shaders, materials, whatever, right? That's all scene assembly. So once you've assembled that 3D scene, you want to send it through to a renderer so that you can come up with an output picture. But there's actually a bit of an intermediary step going from your scene assembly, which is your 3D scene, to an output picture. And that is where the scene description file is being generated. That's the intermediary step, right? So we have a scene assembly, and then it gets translated to a scene description. Now, a scene description is just a set of code that explains to the renderer how certain things should work, right? So it explains the lights in the scene, the cameras, the various shaders, and all of that. Now, this is going to be unique per renderer. If we look at Houdini and Mantra, so we're going from a Houdini scene assembly to a Mantra render, the intermediary step is a .ifd file. Now, that ifd file explains the scene, right? It describes it. It is a scene description. And then that gets sent to Mantra, and Mantra's like, okay, this is the scene description. I can sort of figure out how everything should look. And then it outputs a picture for you. The issue is that different renderers all have different scene descriptions. So if we were using, let's say, RenderMan, that generates a .rib file. Now, sure, there may both be scene descriptions, and it may be the same scene even, but your scene descriptions are going to be different, right? It's almost like if you had to take, let's say, 3 people, and one person speaks French, another speaks German, and then another one speaks Korean, right? And you tell them to all describe the same room. Their descriptions will all technically be the same, but they're all going to be in different languages. They're not going to be able to communicate that to each other. So even though their descriptions are the same, they're not really readable by each other. That's the issue that we have with scene descriptions. Generally, we can't take a scene description and just output it in any renderer because each renderer requires a specific scene description. So this is where we have to start looking at USD, which is Universal Scene Description. Universal Scene Description was created by some super smart people over at Pixar, and it was to solve this issue of having different render engines, creating different scene descriptions, and really breaking down a collaborative workflow. The idea was to create a scene description that can be used in any renderer. But more than that, it was also so that that scene description could go back to a scene assembly, and that could be loaded into any software package. So going back to our analogy of having the 3 people who speak different languages, it's not really like having a translator. It's more like teaching them all a new language. So they learn some extra language that they can all communicate in, right? They now all understand each other. That's the idea behind universal scene description. So what are the benefits of USD? Well, firstly, it is standardized across all DCC packages. That means that we can communicate between different DCC packages. That allows for incredible collaborative workflows. If I give you my Blender file that's been saved as a .usd, you can open it in Houdini, or you can open it in Maya, and you should have the exact same scene. And that's the power of it. You can have incredible collaborative workflows, and that's just one part of it. The collaborative workflow is one thing, but even for an indie studio or someone working on their own as a freelancer, it really does actually help your workflow between software packages or just for scene assembly in general. It's just a very nice tool for ensuring that your scene is well put together. It also minimizes iteration latency. And this is the idea of having to make a change to something and there being a delay in the change. The nice thing with USD is that you can separate it out into layers. So let's just assume that we have a geometry layer, a lighting layer, and a camera layer, right? We have some people working on the geometry, we have some people working on the lights, we have some people working on the cameras. All of those layers get fed into a single USD file that just brings in each one of those things. So if there's a change in, say, the cameras, the new camera gets brought into this file without actually affecting any other part of the workflow. So that allows for easier iteration and less delay on those iterations. Finally, USD is also fairly human readable. I'll be showing you a USD file soon, but just understand that it's pretty much human readable. You can always go into your USD file and break it down and kind of understand it. And that's also kind of powerful in its own way. It allows you to see your scene description right before it goes to the renderer. So you actually get access to that intermediate step that's usually kind of hidden from you. And then, of course, the other powerful thing is that you can take a USD file and you can go either way with it, right? You can take the USD file and you can render it out, or you can take that USD file and you can generate your 3D scene from it. So that means that the same USD file can be opened in multiple different software packages. And that also means it can be rendered out in different renderers. So just like that, USD is incredibly powerful on its own. All right, so in the next part, we're just going to be looking at how USD files are created and what they actually look like when we read them. So let's take a look at that. When we write out a USD file, we're writing out a set of code, right? And that code can be brought back in and it can define our scene. So we can have a scene assembly where all of our things are loaded into our scene, our lights, our cameras, our geometry. Then we can export that to a USD file. And then that USD file can actually be used in another software package or in the same software package. And it'll actually load our exact 3D scene that we started with, right? So it's 3D scene to a USD file, and then a USD file can be used to go back to a 3D scene in any software package. Now, USD files are saved as .usd, but you get USD-A and you get USD-C. Now, USD-A is the ASCII version, and a USD-A file is just human readable. It's a slightly larger file format, and it is slower to load, but you get the added benefit of being able to go inside and read it and change parts of it that you want changed, right? However, if you're working on sort of a final quality USD file, or it's the last step in the process, then you might want to export as USD-C, which is just a binary file. So it's a lot faster to load and it's a much smaller file, but you can't read it, right? So you can't open it up and read it. It'll just be a bunch of nonsense characters. You won't be able to make any of it out. And if you are using Houdini non-commercial, so that would be Houdini Apprentice, then if you try and save a USD file, it'll save as a .usdnc. That just means USD non-commercial. They don't actually allow you to open up that file and read what's inside. You have to have an indie license or an effects license or a core license or whatever. But with an apprentice license, you will be writing out USD-NC and you won't be able to open those up. So if you are using an apprentice version of Houdini, then you can just look at the video and read what I'm showing over here. But if you do want to be working with USD, you are going to have an indie license or better. All right, to take a look at our USD files, you can go ahead and open the files that I've included for download. And this one is one_USD_breakdown.hiplc. So this is the USD breakdown file. Now, when you open it, you may be in the Solaris desktop. If you're not, and you have this view over here, just go over here to this dropdown, and we're just going to change our desktop to the Solaris desktop. you'll immediately notice that we now have these extra panels at the bottom of our viewport, and that's just our scene graph tree. We'll get into that shortly, but for now I just want to show you how we work with USD. So over here we are at the object network, right? And as I mentioned before, we can create instances of other networks. In this case, I've created a LOP network called output_stage and a LOP network called input_stage. That's just if you had to create a LOP network like this, it's just one of these, right? Inside of this output stage, I have a bunch of things. So I'm going to open that up and it'll take a second to load. But what I have is this cube that I've placed. So if I switch my display flag to the cube, we can see that we just have this cube. We have a sphere, we have a material library, a dome light, a camera, and this USD output node. Now the sphere you won't be able to see because it has a transparent material. So all we have to do is switch on smooth wire shaded. You can see it over there. So top right, smooth wire shaded. Now this over here, if we go to the top right of our viewport and we look through our camera. So where it says no cam, just click on that and select your camera. That will allow you to look through the camera. Also make sure that you have your display flag on your camera node so that all of these nodes are evaluated by the time we reach this camera node. Okay, so from here, if we click on this where it says perspective and we go to Karma, we can do a Karma render. So Karma is the renderer that we're going to be using in this series, but what you'll get is just this. And now that background over there where you're seeing the rocks and the trees, that's just from the HDRI. If you want to hide that, you can hover in your viewport, press D, go over to background and disable display environment lights as backgrounds, right? So we just have this. Okay, so we have a cube and we have a sphere, and the cube has a metallic shader and the sphere just a basic red material. If we were to go ahead and output this, we could take a look at the two different types of USD files that are generated. So if I go to my USD ROP over here, we can go ahead and say save to disk. It will evaluate to this location on disk over here. And where this location is can be found by just middle mousing on this output file. That will convert it to a regular path so that you can see where it is. This, when we middle mouse again, is just an expression. So this is just saying wherever this file is saved, inside of the folder where this file is saved, create a geo folder, then create a USD folder, and then take the name of this file. So this one_USD_breakdown, and then append it with .usda, right? So we can see that over there. It'll be put into F drive, life is sweet, geo USD one_USD breakdown.usda. And if I save to disk and then go to that direct location, so geo USD right over here, and I take a look at what's inside this file, you'll see that we have generated a USDA file. Now, USDA is different from USD. USDA is the ASCII version of a USD file. That just means that it's human readable, but it does also result in larger files, and it also results in files that are slightly slower to load. If you want to do a final quality output, so if you are outputting the final version of your USD files, then you want .usd, not .usda. .usd is just the binary version, and that loads a lot faster, and it also saves a much smaller file. However, USDA is human readable. So if we take a look at what we have, there's just some information over here that's kind of defining the basics of our scene. For example, what is the up axis, how many frames per second, all of those things. But if we go down a bit, we start to see some interesting things. Over here, we have a definition for sphere, right? It's a sphere that is called sphere 1. And inside of this, we have a material binding. So that just means that we're assigning this material to this particular object. And over here, we also have all of our materials being defined. So we have a sphere material, and you can see it's got a whole bunch of settings for things like base color. And if we wanted to take a look at this and understand it, we know that our sphere is kind of this orangish red. So if I just scroll down to my translucency color or transparency color over here, you'll see that we have this RGB value, which is 1, 0.5, 0. So this is more or less orange. And that's exactly the color that's being applied to our sphere. And so as you can see, everything that we have in our scene is being defined by just a few lines of code. That's quite easily human readable. We also have our cube material over there. And then we also have our lights. So over here, we have this definition of an X form for lights. And over here, we have cameras. Now we can take this USD file and we can load it back in. So let's go back into Houdini. And that's exactly what I'm doing in the input stage. So if we go up a level from our output stage, you can press U to jump up a level, or you can use the drop down over here, and then just go over to the input stage. All that we're doing over here is using a sublayer node. So if I press tab and type sublayer, you can see that I can use this sublayer node, scroll down to choose the file to load in, and I can choose that USD breakdown. And just like that, it brings in that exact cube and sphere, right? But it's not just bringing in the cube and sphere, it's also bringing in the camera and all of our lights. And so if we look through here, this is the one that's being loaded into our scene. This is the one that's being generated, and they're the exact same. So everything that we have over here is being output to that file, and then over here, all we're doing is reading that file. So we're not reading the actual geometry or the actual sphere or any of that stuff. We're just reading this USDA file, and that's what's being brought in. All of the information that it needs to build the scene is held within this USDA file. And to prove this, we can go ahead back up over here. Let's just find that transparency color. So trans color. And let's go ahead and change this. So we know that this is an orange color, but let's maybe make this green, right? So that would be RGB. We can just do 0, 1, 0. So this is a new RGB value that we're giving it. We can save it. So Control S to save. If I go back over here and just tell it to reload this file, you'll see that it's now green. So now we know that it's actually loading this from that USDA file, and it has nothing to do with this output stage over here, right? It is now just loading it from that file. Right, so in the next part, we're going to be looking at how to take things from the object level and bring it into a LOP network so that we can then output it to a USD file. So let's go ahead and look at taking things from an object level scene assembly to a LOP network for USD export. All right, so in this part, we're just going to be looking at how USD is kind of formulated and some of the terminology that we use inside of Houdini and inside of USD. Now, keep in mind that a lot of the terminology that we're going to be using inside of USD is specific to USD. So if you hear something like a primitive, that doesn't necessarily have the same meaning as it does in 3D, right? So let's actually start with that example. In USD, when we say a primitive, we're just talking about any element in our 3D scene, right? And so they don't mean primitive in the way that we mean primitive when we're talking about a piece of geometry or like a face. When they say primitive, it's more of the literal definition of primitive, which is like basic, right? It's the most simple version. So the most basic element of your scene is called a primitive, and a primitive can be anything. So that can be a light primitive, a camera primitive, a mesh primitive. You can have a primitive for pretty much anything inside of your scene. So each one of those primitives also have a primitive type. Now that type could be something like a camera, or a dome light, or a rectangular light, or something like a mesh, right? But there's also two others that I just want to bring up, and that is XForm and Scope. Now XForm and Scope, you can almost think of as just a parent for some other object. You can view it almost as a null in other 3D packages. So let's say you have a primitive, and that primitive contains a cube, right? So this cube is parented under this primitive. If we move that primitive around, then that would be an XForm, right? So an XForm is just a primitive that's able to move. However, sometimes we want to nest things under a primitive, and that primitive doesn't need to move. In the example of, let's say, a material. Materials don't actually physically exist anywhere in your scene, so we never need to actually move them around. That's where we use a scope. So we have an XForm and we have a scope. That's just the two types that aren't really self-explanatory, but you really don't even need to know those. I just think it's maybe interesting if you are interested in it. So we also have kinds. Now, a kind is just a tag that USD uses to let us know what this is in our scene. So there's a couple of different kinds, but the ones that I want to focus on are just components, assemblies, and groups. A component can be thought of as a single composed asset, right? Now, if we're looking at something like my desk over here, this could be a component, right? The mouse, that could be a component. The mouse pad could be a component. This keyboard could be a component. But all of these things that I have make up an assembly. The assembly is perhaps my workstation, right? So all of those components make up the full assembly. So that's the explanation for a component and an assembly, right? Components are these little constituent parts, and an assembly is where we just bring those together to make a larger asset, right? Now, when we look at groups, we're just looking at some sort of arbitrary grouping of things. So perhaps I want to group all the electronics, right? So now I'm including things like my light, my microphone. Now it's all of these things as well, right? So it's just an arbitrary grouping of different things. So we know that we can group things that are kind of familial or related, and that's how groups work. So just keep that in mind. We're going to go straight into the tutorial now. But those are just some concepts that I thought I should mention ahead of time. Right, for this one, we're opening to_Solaris_basics, and this one just has a scene assembly that has been done at the object level. As you can see, I'm already in the Solaris desktop. If you're not, you can go ahead and click on this dropdown over here and just switch to the Solaris desktop. Okay, so over here, all I have is this lollipop geometry. If I dive inside, I've just generated a lollipop using a couple of nodes. You can see that this is the lollipop head, and it's been given a name called lollipop_round_top, and over on the side is a stick as well. This one has also been given a name. Now, in Houdini, we have various attributes to describe the data that's coming in from different sides. So for example, we need point positions, we need things like UVs, normals, colors, all of that. So all of those are stored as attributes, and we can actually see this if we middle mouse on a particular node. You can see that we have a point attribute, we have a primitive attribute, and we have a vertex attribute. So point attribute P is just position, primitive attribute name is this one that we've created over here, and then of course your vertex attributes, UVs, are just UVs. So this over here, where we define a name for each one of our chains of geometry, is going to become important a bit later, but for now just understand that all we're doing is we're assigning a name attribute and it has this particular value, lollipop round top and lollipop round stick. Then we merge those two together once we've assigned materials to them. We bring it up above the ground plane, and that's our output, right? Just like that. Over here, we just have a ground, that's just a grid. And then we have an area light over there, and an environment light over here, a camera, and a material network. Inside of the material network, we just have a material for the lollipop, for the stick, and for the ground. So this is how you would usually do scene assembly within Houdini. And then what you would do is you would go to the out network and you would use, say, a mantra node. And from here, you could render to disk, right? And that would work. You can still do it. It'll work with the scene as well. However, the new renderer, Karma, works a bit differently. So if we drop a Karma node, we now have access to the new renderer inside of Houdini. So Mantra is the old one and has been replaced by Karma. Now, Karma does things slightly differently. Of course, we can still render to disk or render to mplay as we would with a Mantra node. However, we also have this option for a Karma viewport. If we click on that, it brings up this extra window over here, and it has its own viewport. You'll notice that it'll also start rendering. It'll just start rendering in this Karma perspective over here. And if we select a camera, so if we go over here and just select our camera 1, we can also look at our scene through the view of our camera. We can switch back to the regular shaded view, just like this. So we have this viewport. And again, you can switch to the Karma render view. Okay, so what's actually happening here is that this is once again creating an instance of a LOP network. As we mentioned before, we can create instances of networks. However, this is hiding a lot of the things behind the scenes. As you can see over here, this is our path for where this is found. You can see that we have the out network. So that is this network over here. And then we have Karma 1. So this Karma render node. But then you can see it's actually generating two layers underneath that. It's generating a LOPnet and a Karma node. And what's interesting about that is that it's taking all of our objects in our scene, converting it to a USD standardized set of lights, cameras, geometry, and materials, and then it is allowing us to render. So if we were to do that ourselves, we could. So instead of doing the out network Karma viewport, let's go ahead and go to the stage level. So using this dropdown, just go to the stage network right over here. And as you can see, I've already set up some stuff for you, but it's nothing too complicated. On the left over here, we just have the scene import all. We can very easily drop one of these ourselves. As you can see, we have the scene import node. Alternatively, we also have some variants of it. There's the scene import where we can choose what we want, or there's the scene import and it says all, that brings in all objects from our object level, or just cameras, lights, or materials, right? So we can bring in certain things based on these presets. I'm just using the scene import all. If we click on it over here, you'll see that the objects that it's bringing in are defined by this asterisk. And that just means that it's bringing in everything, right? Asterisk means everything. So star inside of Houdini just means everything. And if we take a look over here by using this dropdown, we can see that it is selecting area light, camera light, environment light, ground, and round lollipop. If we hold control, we can deselect certain things or select certain things. So if we say we don't actually want the ground, we can accept that pattern. It changes it from a star to just the things that we want to bring in, and they're space separated. So you can see that the camera over here is separated from the area light, separated from the environment light. Alternatively, once again, replace that with asterisk to just bring in everything. If we scroll down further on this node, you'll also see down here that it imports our materials. So that means that our ground and our lollipop are also receiving materials. And so that might seem good to have everything being brought in all at once, and you can render from here, right? So if you prefer the old method of doing your scene assembly up here and then just rendering out, you can just use a scene import all, and really it should work pretty well. It's basically what that's doing when you go to the out network and do a Karma viewport. It's just bringing in everything. It's not doing any sort of scene assembly at the LOP network level. It's basically just taking everything at the object level and shoving it into a LOP network in a very brute force kind of way. So what do I mean when I say a brute force kind of way? Well, if we have all of our objects in our scene like this, if we take a look at the bottom left, you'll see that they haven't been organized in any particular way. We have an area light, a camera, an environment light, a ground, we have this OBJ thing over here, and a round lollipop. Now, this over here is your scene graph tree, and you're going to be spending a lot of time using this when working inside of Solaris and working with LOPs. So, from here, we can enable things and disable things, so we can do things like disable the ground, right? So if we were to render now, we no longer have the ground. It is still there, and you can see that it has this little red dot next to it. And we can actually see what that means if we go to the top right over here. We have this legend. We can bring it up, and we can see that we have a viewport override. That means that we've overridden something about this, right? All we've done is we've disabled it, so that's how we know we have an override. We can re-enable it, and again, it'll render with it. All right, so these over here, you'll notice that some of them have this little plus icon next to them. That just means that they're comprised of something else, right? So they're a parent to something else. If we take a look at this ground, it's actually a parent of a mesh. And this might seem a bit strange, but it maybe makes more sense when you look at the lollipop. The lollipop is a single asset, which is made up of two pieces of geometry, the lollipop round stick and the lollipop round top. And it's actually splitting this up based on that name attribute that we created. That's something that this does, which is kind of smart. It actually separates things based on a name attribute. So if we go down over here, you can see that it says path attributes. And by default, it's actually doing this. If we enable it and we remove this, you'll see that it brings it in as one mesh comprised of two materials, right? And if we were to hide this, we can only hide the entire lollipop. But if we have that path and name attribute, so name is the one that we have, it actually splits our geometry up. So it's just a smart way of letting it know that, okay, this thing over here is one piece of geometry or one subset, and this thing over here is another. And now they are brought in as two separate pieces of geometry, but still as part of a single asset. So these things over here that we're bringing in are all called primitives. Now, if you have an understanding or a background in 3D, using the term primitive to describe just anything is a bit strange. But understand that this is a terminology that's directly from USD, and it varies a bit from our general 3D understanding. So for the duration of this tutorial series, kind of just push your current understandings aside and look at it through the scope of USD. So when I say a primitive, I mean a USD primitive, not a usual piece of geometry kind of primitive. And in USD, what a primitive is, it's just any element that we've brought into our scene. This area light is a primitive, our camera is a primitive, this ground over here is a primitive. The lollipop's a primitive. Each one of its meshes that make it up, those are primitives as well. And we can actually see that over here. Each one of these has a primitive type. This area light is a rectangle light. This is a camera. This is a dome light. But this over here is kind of interesting. This over here is an X-form. And the only two that I really want you to focus on is X-form and scope. X-form is just a holder, like a parent. And it parents certain primitives underneath it. For example, this ground X-form parents a mesh underneath it. An X-form is just something that you can move around. It's almost like a null. And if we had to parent things underneath it and then move the X-form, everything that is parented under it shares that transformation, right? And this is also true for this lollipop over here. This lollipop is an X-form primitive, which is comprised of two mesh primitives, right? So each one of these meshes fall under a single X-form. And you can move this lollipop around. That's why it's an X-form. However, you also have something like a scope. If I expand this, you'll see that this scope over here actually contains our materials. And a scope is an X-form without the ability to transform. And if you think about it, it's basically just a primitive that doesn't ever need to be moved around. For example, materials don't really physically exist in our scene, so we never need to move them around. Actual pieces of geometry need to be moved around, so they get put in as X-forms, while things like materials get put under scope. So that's just to clear up those different primitive types. The rest are pretty self-explanatory, right? Like a camera, a dome light, and a mesh. Scopes and X-forms are the only things that are a little bit different. Okay, so that's just if we do it with a scene import all, but that actually limits our control quite a bit. As you can see, we don't have much control over this hierarchy, how it's comprised and how it's made up. So a better way to do it is by using SOP imports as well as using scene imports. So if I use a SOP import, I'm just going to drop one over here. You can see that this node over here allows us to choose a particular SOP path. So if I use the dropdown, I can select say just the round lollipop and say accept. That will bring in just the lollipop, right? You'll see there's no materials on it, nothing. And the name that gets assigned to it in our hierarchy over here, in our scene graph tree, is just sub import 1. What it actually takes is the name of the node. So if I were to rename this to lollipop, you'll see that it fetches it over there. It's actually called lollipop1 because I already have something called lollipop, so it just appends a 1 so that the two names are unique. And that's actually a pretty good understanding to have. The reason why we actually want our things named after our nodes is that node names are always unique. So you'll never have a conflict of names. For example, this one over here will be called lollipop, but this one over here will always be called lollipop1, right? So if I had to make duplicates of this, it'll just append this number to the end. So I never have conflicting names. Now, where it's fetching this from is actually over here. Under this import path prefix, we have /$OS. $OS just means the name of this node. Once again, we can see what it evaluates as. If we just middle mouse on this over here, you can see that it evaluates as /lollipop1. Now, that means that we can make changes to this. So let's actually go ahead and create a geo primitive that holds all of our geometry. So we can actually go /geo $OS. And what this will do is it will create this geo primitive over here. And inside of that, we'll have our lollipop. And inside of that, we'll have these two pieces of geometry which make it up. So to avoid this lollipop1 name, we can just call this round lollipop or something, right? Okay, so there we go. We have geo, and inside of geo, we have round lollipop. And that's literally all we're doing over here in this longer chain. We're bringing in the ground, we're putting it in this primitive called geo, so /geo. Then we're doing the same thing with the lollipop. We're doing /geo, but this time we're adding a lollipop instead of a ground plane. So you can see that now under our geometry over here, we have a ground plane and a lollipop, and it's all nicely nested under this little geo primitive that we have. We can then import our cameras. And as you can see, we once again have paths and things that we can set. So over here, we just have cameras being brought in, and inside of there is camera 1. We also have the same thing for our lights. Once again, our lights, we have our area light and our environment light. Down here, we also have our materials. So we're bringing in our materials separately. And as you can see, that adds this little scope over here. Under OBJ, we have these materials: ground, lollipop, stick, right? So now, as you can see, we've now separated everything into primitives. And each one of those primitives has a little drop down for everything that applies to it, right? Now, it's really easy if we want to, say, take a look at just our cameras or just our lights. And then the only other thing that is different with this is that I'm actually assigning a material. So instead of having our materials automatically assigned, we can actually assign it ourselves. So if we use an assign material, I'm just going to drop one over to the side. It's super basic. So in this situation over here, I have this assign material node. None of our materials are currently assigned. And all we have to do to assign a material is drag over the primitive that we want the material assigned to, as well as the material path. So let's go ahead and expand our geometry. We'll expand the lollipop top over here, drag it over. That's the primitive over there. And then the material that we want to drag over for it, lollipop material. Just like that, it gets assigned. And then we can do the same thing over here if we want to do it for the stick. And then drag over the stick material, add another assignment for the ground, drag over the ground. You can drag over the mesh or the ground. If you drag over the ground, then it gets applied to everything that's inside of it. If you drag over just the mesh, then it gets assigned just to the mesh. So it's usually safer to just assign it to directly what you want it assigned to. And then we can go ahead and drag over the ground material, just like that. So it's now made these connections, and that's all I'm doing with this assign material at the bottom here. And once you have that, you now have this scene that's been nicely composed, right? As opposed to this over here, where it's a little bit all over the place, and we don't have much control. Over here, everything is very neatly set up. All right, so the only other thing that I would like to mention very briefly is just this over here. So we know primitive type. We have these X-forms and scopes and all of those things, and inside of there, we have particular objects, but you'll notice that some of them get these unique icons, right? And on the side over here, they also have this kind. You'll see that this one is a group, this one is a component, and these are just tags that help us understand what this thing's role is within our scene. For example, we know that this geo is a group of different geo components. And I think that's fairly self-explanatory. A group is just an arbitrary collection of related things. So for example, you can have a group for your lights, or you can have a group that contains every type of tree in your scene, right? That kind of thing. It's just a group of things that are related. In this case, it's just a group for all of our pieces of geometry. You will also notice that these two over here are called components. Components are just kind of finished assets. So if you were to think of a house, and in that house you had a door asset, well, that door can be considered a component, right? It is a single asset in and of itself. However, when we start adding things like windows and a roof and sort of objects within the house, then that becomes an assembly. So an assembly you can think of as a bunch of different components that all come together to create a single asset, right? And those are just the three that you need to know. So a group is just an arbitrary grouping of related primitives. A component can be considered a composed asset. And then an assembly is a bunch of assets all combined. Okay, so now that we've got the technical stuff out of the way, we can start looking at how to actually start building scenes and things inside of Solaris. We just need to have this kind of base level understanding of how our scene graph tree is built up, what primitives are, what primitive types are, and what primitive kinds are. Over and above that, we also just needed to look at how to bring things in from the object level, as well as how to assign materials. So if you need to come back to this file, feel free to open it up and use this as reference. I have included all of these notes so that you can see exactly what everything is doing. Okay, let's move on to the next part. When we create our scenes inside of Solaris, Solaris is a USD context. So anything that we create inside of the context is conformed to USD standards. When we drop a camera, it's not just a regular Houdini camera, it is actually a USD camera, right? So all of the settings on the camera, when written out to USD, will all conform to the correct standards, and when you import it into another scene, it'll all import perfectly, right? That's the idea with Solaris, is that any single thing that exists inside of Solaris should conform to USD. So if you save it out to a USD file, you can load it in any 3D package. So this is also why we choose to switch to the Solaris desktop. In the Solaris desktop, you can see at the top where your shelf tools are, that it limits what you can place into your scene, right? And that's because it only limits it to what's allowed inside of Solaris. But every single light, camera, geometry that you place inside of the Solaris context is USD conformed, and it will write out to the USD file correctly. So let's go ahead and see how we actually build those files inside of Solaris. Okay, go ahead and open up 3_Solaris_stage_building. This file is just going to show us how to actually create a scene assembly at the LOPNet level, or at the stage level. So what we have over here is just this spiral lollipop geometry. And this geometry over here is all we have, right? There's no cameras, there's no lights. All we have is this piece of geometry, once again, very similarly to what we had before. If it's difficult to navigate over here, hold space and press F. That'll just focus in on this object or whatever you have selected. You can also press space plus G. It returns you to your home view. So space plus F will just focus on whatever you have selected. Okay, so once again, it's much the same as what we had in the previous part. And so we could take this to the stage level. If we go to the stage level, we can use a SOP import as we've done before, right? So this is the same as using that SOP import that we looked at before. And then you bring in that lollipop. And then all you do is do /geo over here so that it puts it into a group. And right over there, you have this group, right? That's all I'm doing over here. We have /geo $.os, which evaluates to /geo /lollipop based on this node's name. Okay, so then we can go ahead and add a ground plane. Now you'll notice that this ground plane is curved and it doesn't actually exist at our object level. So where is it coming from? What we can actually do is use a SOP create node. And a SOP create node, if I dive inside over here, you'll see that it actually allows us access to all of the things that we would have access to at the SOP level. Now the SOP level is just this level over here, where inside of here we can create this lollipop, right? There's a different set of nodes for that. And when we create a SOP create node like this, we have access to those nodes inside of here. So all I'm doing in this situation is inside of here, adding a grid, and then using a bend node to kind of bend it up. And that over there just gets added as a node. And so now we have a ground and a lollipop. You can see that once again, I'm doing that same sort of thing where I'm doing /geo $.os. And again, it evaluates to /geo /ground. So again, we have this nice little group, which is an X form. Inside of there, we have these two X forms, which are components. And inside of each of those, they have the meshes that make them up. All right, we then have this camera over here. And this camera has just been placed right over there. If we set our display flag on it, we can look through the camera. And the way that you place a camera at the Solaris level is just by clicking on the camera icon at the top in your shelf tools. So if I navigate to a place in my scene where I'd like this camera to be placed, I can then very easily just press camera and it'll add a camera at that position, right? You can see it's added it over here. Alternatively, if I were to click Control and then click on the camera, you'll see that it sets it to red. All that means is that this camera is locked to my view. So if I move around in my scene, my camera will move with me, right? So I can make edits to my camera in this way. And to disable that, all you have to do is disable the lock over here. Once you do that and you start moving, you'll notice that it no longer locks to your camera. My camera is now staying where it should, and I'm free to navigate the scene as I'd like. All right, so that's all I've done with this camera one over here. Then we have two different options. On the right-hand side, we have a material library with an assigned material. And I'm going to show you this one first. What we're doing in here is creating three different materials. We're creating a lollipop principled shader, we're creating a lollipop stick material, and a ground material. All of these are principled shaders. So this is the same thing as if you were at the object level and you were to create a material network. You would create a principled shader, and this principled shader could just be whatever, right? This could be like your lollipop shader, just like that. And so it's the same thing, but now we're doing it at the stage level. So over here in our material library, you can see that we have these three materials. This one on the left is a little bit more complex than the other two. And that's simply because we are using these two texture nodes over here and a color mix node to blend between two different colors. So this texture over here is just an image that I'm fetching from disk. It's just a black and white spiral pattern. And then I'm using it as a bias to blend between red and white. And so if I look at the lollipop through this camera and just do a Karma render view, setting my display flag on the assigned material, you'll see that that's what we have, right? That's all it's doing. So it's using the texture that's coming in as a mask to drive between two colors. So we can change the two colors if we want, just like that. Then we also have this texture over here coming into the roughness. And finally, down here, we have this displace texture. This is a slightly different node. So these two up here, these are just texture nodes, right? So we just have this texture node, and this texture node, you choose a texture map. With the displace texture, you can see over here, we have this displacement texture. And the only thing that we need to do to change this to work with normals is instead of using displace along normal, we switch this to normal. That's how it knows that this is a normal map. So over here, we have a normal map, texture type normal, and the effect scale. So that's just how much is our lollipop affected by this scale. And so if I go up a level and I take a look at this material library, so display flag on the material library, you'll see that these materials all exist, but none of them have been assigned, right? And if your materials don't exist, then all you have to do is say autofill materials. So I'm going to clear this as if this node were default. All you have to do is click autofill materials. What it'll do is it'll detect every unique material inside of this library and add it into your scene graph tree. How does it know what to add? Well, it just looks for these little orange flags over here. So you can see that all of these nodes over here don't really have it, but our actual shader nodes do. So if you want to hide a particular shader from being autofilled, you can just disable its flag. And then if I clear this and then autofill, you'll see I only get two because this one is being ignored. I can activate it again, autofill, and I get that third material. Okay, so these three materials exist, but then I still need to assign them. So I go to the assign material over here, and as we've done before, we drag over our mesh for our ground, we drag over the lollipop spiral stick and the lollipop spiral top, and then we drag over the materials for each, right? So that's exactly what we've done over here. You can see that the stick gets the stick material, you can see that the lollipop top gets the lollipop material, and you can see that the ground gets the ground material. Now that's one way of doing it, right? And this works. If we take a look at our switch node over here, and I just switch to this chain of nodes, if we go down here and we render, that works perfectly fine, right? So our materials are all coming through, they're all being assigned, and that works perfectly fine. Alternatively, if you would prefer to do it all in one node, you can do it with this material library node on this side. So on the left-hand side, I've done something slightly differently. Instead of adding an assign material node, I'm doing the assignments directly on the material library. What you can do is you can autofill all of those materials and then just drag over the geometry under this assign geometry. So you can see over here, we have this assign to geometry option. All you have to do is enable it, and then you can just drag over your various geometry primitives to assign the material to those primitives. As you can see over here, I've dragged them over. We have the spiral top, the spiral stick, and the ground mesh over there. And let's just go down to this last node over here and switch to the Karma render view. And if you switch between these, you have the exact same thing, right? So in this case, we're just assigning using two different nodes. In this case, we're assigning just using the material library. So you might be wondering what the benefit is to actually assigning your materials separately. Well, let's just say you were bringing in your materials separately and you didn't have access to the geometry. Then you could do something like this. So let's just imagine that my geometry is running down one chain like this, and my materials are in another chain, and I want to merge my materials in just like this. you can see that I've now included my materials. They're now part of this chain, but they haven't yet been assigned. So I've worked on my materials on the side, and then I'm bringing them in. Maybe someone else is even working on my materials, and I'm importing them in. And then what I can do is I can use this assign material node to assign all of those materials to my geometry. Just like that, right? So that's the added benefit, because you can actually have your material library off to the side, not actually directly assigning. You can bring it in to be joined with the rest of your geometry, and then you can assign it separately, right? Just like that. And all of these down here, these dome lights, area lights, they can also all be brought in from the shelf tools at the top. And understand that these are all USD standardized. So if you open this in Maya, these lights should all have the same sort of intensity and exposure. If you open it in Blender, same thing, right? Everything that is happening over here in this chain, when we open the scene in another 3D package, everything should be exactly the same, right? Our lights should have the same positions, our camera should have the same settings, so things like focal length and aperture and all of those things should all be the same no matter which piece of software we're using. The only thing that is specific to Houdini is the materials that we're currently using. So these materials over here are Vex-based materials, principal shaders. These are ones recognized by Houdini. So if you were rendering in some other renderer, so let's just say we take the scene and then we take it to Arnold, you would need to have separate Arnold materials that you can then assign to all of these pieces of geometry, right? So everything else would work. Your lights, your cameras, your geometry. The only thing that won't work are your materials. They are dependent on the renderer. But we're going to be looking at MaterialX soon, which is the workaround for this. It's almost like USD, but for materials. It's like a universal material. So we're going to be looking at that very shortly, and that kind of solves that issue. Okay, let's move on to the next part. If this tutorial series is helping you so far, please go ahead and subscribe, leave a like, and if you're really enjoying this and you feel like it's given you a lot of value, then please go ahead and hit the join button. Just any small contribution really helps, it all adds up. And yeah, it's just really nice when people show their love. So let's go straight back into the tutorial. Inside of USD, oftentimes we want to build assets. And when we build our assets, there are a couple of things that come together to create an asset, right? So we have a geometry, we have a material, we bring them together, and then we output them, right, as a .usd asset. Now that asset in its most basic form is literally just that. It's a geometry, it's a material, and it gets output, and those two things are kind of contained together in a single asset that can be loaded into any sort of 3D package that uses USD, and you will have that same material and that same geometry. However, USD allows for something called variants, and variants are a more advanced asset. What it allows is for you to take multiple geometries, plug it in, save it as a single asset, and then once that asset has been saved out, you can switch between those variants that exist inside of that asset. So let's take an example of a cup, right? Maybe I have 3 different geometries. One's a styrofoam cup, one's a plastic cup, and one is like a mug, right? So it's like porcelain or something. Those 3 can all be saved in a single asset. Maybe that's called like a mug asset. Then when we load that mug asset into a scene, we can actually choose from one of those 3 variants. So perhaps in this scene, I want the styrofoam one, so I can just choose it. Then over there, I want the porcelain one, so I can just select it, right? It's that simple. You have a single asset that contains all of your variants. But variants can be more advanced than that. Variants can also contain different materials. You could have a porcelain material, a styrofoam material, and a plastic material all saved into that asset, and each one loads their respective texture. Or alternatively, you can get creative with it, and you can have it so that maybe the styrofoam cup has access to like 3 different colors or something. And so there's all sorts of interesting things that you can do with variants and USD assets. Now to make a USD asset, we're going to be using the USD component builder. So inside of Solaris, we're going to be using that. And all that does is what I just mentioned, right? It brings in some geometry, it brings in some materials, combines them into a single asset and saves it out. So I'm going to be showing you how to do that now. For this part, you can go ahead and open up for_component_building. When you open up this file, you'll see that we have 2 object level geometry nodes. And inside the one, I just have a bunch of suites. So these are just being generated over here in a usual Houdini network. We have a gumdrop, a Smarty, and a jelly bean. So the point of this part is to show you how to take these kinds of assets and actually convert them into USD conformed assets that we can just bring into our scene, right? This becomes extremely useful for when we just want to import a ready-made asset. And this becomes extremely powerful, especially if you're working in a studio or in some sort of extended pipeline where somebody needs to prepare an asset for you and then you need to bring it in, or you're the person preparing the assets for the USD pipeline. So this is going to show you how to do that so that everything conforms to the standards that it needs to conform to. So we have this sweets geometry and a lollipops one over here. The lollipops one we're not actually going to use. You can use it on your own to experiment with this. But I'm going to go over to the stage level where I have a bunch of different networks. So Houdini recently introduced the component builder. Before the component builder, it was quite difficult to put together USD conformed assets. But we now have the component builder and we don't have to worry about a lot of the stuff that it's doing behind the scenes. So I'm going to show you how to use that. So all you have to do is type component builder and it'll actually drop 4 different nodes for you. You can see them over here. On the left hand side, this is the geometry to bring in. On the right hand side, it's the material to assign to that geometry. Over here is where the actual assigning of the material occurs. And then over here, we can output that to disk, right? We can output that asset. So let's just try this out, right? So over here, I'm going to set my display flag on the component geometry. Over here, I'm not going to use an internal SOP network, but an external SOP. That just allows me to choose what I want to use. And then I can just extend my OBJ over here and then extend suites and choose just the gumdrop, right? So we're going to work with the gumdrop first. So now we're just bringing it in, right? So external SOP, choose the particular node that you want to fetch from this network. You'll see that I have out gumdrop, out jellybean, and out smarties. Those are actually just nulls inside of here, which just let me know which ones are the output nodes. If you capitalize the name of a node, then it appears at the top when you're searching for it in your hierarchy. So over here, out, 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 those 3 are the ones that show up when we go to the stage level, right? Right over there. So I'm just choosing the gumdrop, and I can choose a proxy and a sim proxy. A proxy would just be a low resolution version of this for preview purposes. So you could bring it into your scene, and it would be a stand-in for the actual geometry. Same thing with sim proxy, you can use that for simulation data. So if you need to take a scene and then use it for a simulation, you can use the sim proxy, which somebody has included inside of the asset for you, to actually run all of your simulations. So you can use it as a collider. And that's all we really need to do on here, right? One thing that I will mention to you is just this over here. It does actually use this component geometry too, so the name of the node, to create a variant name. And that's going to become apparent later. But for now, you can actually just call this gumdrop variant. I'll explain variants later, but that's just a useful thing to do, right? Name it after what it is, and then just suffix it with variant. So that's gumdrop variant. Over here, the material library, we'll want to create a material for this gumdrop. So I'm just going to go in here and create a super basic material. You can see over here, I've done the same thing. So all I have to do is go inside, and we'll just use a principled shader. I'll call this gummy material, all right? And over here, I'll just give it some base color of a greenish color. And I'll go down here to the subsurface scattering and again, give it this sort of greenish color. I'll also set it to single scattering and decrease the distance for my subsurface scattering. So it's a small object, so I would want to have a lower distance on my subsurface distance. I can go up a level, and now what you'll notice is that this material library doesn't need to be auto-filled, because what it's actually doing is it's fetching every material inside here. You can see it has this asterisk, so it's fetching every single material that has this orange display flag on it. You can see over here that it's already added our gummy material. Now, when we see this over here where it says asset, right, you can see that asset contains geo. And inside of that geo, we have our gumdrop. As soon as we go to this component material, it now also has the material. So all this component material is doing is kind of combining these two streams, right? It's taking this component geometry, which is called asset, and inside of the asset, we have our geometry, and now it's adding the materials to this asset primitive as well. And what it's doing over here, once again, just middle mouse on these to see what they evaluate as. What it's doing is it's saying, okay, so for everything inside of geo, right? So everything inside of this primitive over here, apply this material. So it's automatically applying the first material that it comes across to this over here. So if we have multiple materials in here, it will just find the first one. And the first one is actually based on the name. So if you have another material over here, and I just call this one a gummy, so now we're looking at alphanumeric, so gummy and a gummy, then you'll see over here that it actually assigns a gummy. If we take a look over here, yeah, so you can see asset mtl/a gummy, right? So it's using alphanumeric, so the first thing that it comes across based on the letter is the one that gets applied to all primitives that are coming in. We can adjust this, we can set this to our own primitives and things like that, but usually the default's fine. So we can just remove this a gummy, and once again, it'll switch back to the other one. Then all we have to do is actually just save this to disk, right? So you can see over here, if we see what all of these evaluate as, it's not a great naming convention, right? It is using this component output name a lot. And most of these nodes actually use the node names. So even this component material over here, you can see that it's actually using this OP name. And again, check what it evaluates to. It's evaluating to the name of the node. So just change the name of the node to gummy material variant, right? So once again, this is another variant. And we'll once again be getting into explaining variants shortly. But we have this gumdrop variant and we have the gummy material variant. And then if we now go down over here to this component output, we could save this to disk, right? And again, we'd want to change this name to something like gumdrop underscore asset. So now what this evaluates to is gumdrop asset. It'll create a gumdrop asset.usd file at this location. So if we save this to disk, it should create this over here. And I can actually go find that. So USD assets, gumdrop asset, USD assets, gumdrop asset, right? And what you'll notice is that it actually creates a couple of USD files, right? Sure, it creates this gumdrop asset, but it also creates this MTL USD and this geo USD. Now, these two are fairly self-explanatory. These are separate layers. It's creating a geometry layer and a material layer. And then this gumdrop asset just references those two. You'll see this is only 1 kilobyte and the material is 6 kilobytes and the geo is 203 kilobytes. So this is actually just a reference to those two. It's bringing them together into a single asset. This payload asset is actually just a bounding box. So if you want to unload something from your scene and just represent it as a bounding box, this just stores the information for that bounding box. I'll show you that at a later point, but you can unload assets. So now that we have that, right, we can actually just work with it from here, or we can load it into our scene. If we want to load it into our scene, all we have to use is a reference node. So we can drop a reference node, and a reference node allows us to fetch a particular asset. So we can go over there to USD assets, gumdrop asset.usd. And as you can see, as soon as I switch my display flag, it's the exact same thing, right? So it's now referencing it in. You can see over here, it has its geometry and its materials all inside of it. So that's just how you create an asset. It's super simple, right? You bring in the geometry, you give it a material inside of this material library, and then you just need to rename these to whatever geometry that is, underscore variant, whatever material this is, underscore variant, and then whatever the asset name is. So you're just renaming those 3 nodes over there, and that's all you're really doing. There's not that much to do on this node. Everything else is kind of done for you. The other thing that you can do is generate a thumbnail. And the thumbnail actually is kind of useful because if you want this asset to be loaded into an asset viewer, which you can do, and I will be showing you, what you can do is you can say view thumbnail camera, and it'll set this to a temporary camera. And then you can just say generate thumbnail. And all this will do is just save a little thumbnail of this asset, right? You can see over here, it just saved this image out so that when I actually add this into my scene, I can actually see which asset I'm bringing in. And you can actually change this from like a viewport render to an actual render. And then if you generate that, it'll run a Karma render, which will actually render this over here. If we take a look at it now, you can see that that's what it will render as. You can, of course, add lights and things to generate it properly. But yeah, that's just the basics. Okay, so then what is all of the extra stuff over here? So this one over here is actually really cool. We have 3 different geometries that are all being brought in. And then we also have 3 different materials. And each one of these are being assigned differently. And over here, we now have a single asset that has access to 3 different materials and 3 different geometries. Now those are variants. We have 3 different geometry variants, 3 different material variants, and they are all stored within one asset, and we can access all of them. So before I show you how to access all of them, let me show you how to create this. So over here, where we have our gumdrop asset and our little material library, we can actually expand upon this. So this gumdrop variant node over here is actually a component geometry node, right? One like this. Now we can place our own one, or alternatively just duplicate the one that exists by holding Alt, clicking and dragging. That will create a new one. And then we can just select our jelly bean, right? And we can call this jelly bean underscore variant. Then we'll hold Alt and click and drag over again. And this one will be our Smarties, and we can call this Smarties underscore variant. Okay, so now we have 3 different geometries, but only 1 input. So what we have to use is the component geometry variance node. So component geometry variance, and then just plug each one of these into here. What this will do is it will add all of these into a single variant set. So if we take a look at this, you can see that it says variant set geo. As a part of this variant set, we now have 3 pieces of geometry that we can switch between, and that'll work perfectly fine. What happens when we go over here is that this material actually gets assigned to everything inside of asset, right? So it doesn't just get assigned to just the gumdrop, it actually gets assigned to all three of them. And we can see this, right? So this is the exact same thing as we had before, but now let's use an explore variance node. So explore variance. And just like this, we can go ahead and say explore variance and reduce the spacing between them to like 0.1. And if I just move around over here, you can see that I actually have three geometries that are all fetching that same gummy material, right? And these are variants. So within this gumdrop asset, we have these three variants. And this is extremely useful. You can actually take this and you can randomize instances and things like that. So let's say, for example, you have a house asset and the doors on the house are assets of their own. What you can actually do is you can store variants of each door. And then you can go ahead and in your scene graph tree, you can select a particular door and change which variant it is referencing. That means that you can easily switch assets in and out, and they're all contained within a single asset, right? So within the single gumdrop asset, I actually have three different assets that I can switch between. But this isn't exactly how we want it, right? We don't want it so that all of them have the same material. So this is where we're going to have to make a few changes to this area over here. If we open up this material library and just duplicate this gummy material over, we can make a coated gummy material. So that might be something like a jelly bean. And then over here, we can just do a hard coated material. And the gummy coated material, I'll just add coating to it. So let's go over here to coat and add a coat and maybe increase its actual roughness a bit. So its specular roughness is a bit higher. And then let's also just change its color so that we can see it. So let's change it to this pinkish color. Over here on the hard coated material, we'll switch off our subsurf scattering. We'll go up to the top and just give it a base color of something like blue, and then reduce its roughness to 0. Again, we can also just add a coat, something like that. And one other thing, let's just change the base color on our coated gummy material to something like pink. And you'll immediately notice that these over here have turned pink. That's because, remember, coated gummy material, alphanumeric, it's picking up this material and just assigning it to everything. So we actually don't want it to do it this way anymore. What we want is we want every material to be assigned to every piece of geometry. So how do we do that? So let's be specific about this. Instead of this material path, which is evaluating as the gummy material, let's tell it, okay, this one needs to be the regular gummy material, right? So we have that one gummy material variant, and then we can create more. So let's Alt, click, and drag to create another material over here. And this one over here, we're going to drag over the coated gummy material, just like that. And then we're going to Alt, click, and drag, add another one. And this one over here, we're going to call hard coated material. And then we just need to change the names so that they match. So we can call this one coated underscore gummy material variant. And we can call this one hard underscore coated material variant. And what you'll notice is that as we were busy with this explore variance node was busy changing. And what it was doing is that it was expanding all of the possible variants that we could end up with. We now have access to 3 different materials and 3 different geometries. Each geometry has access to each material, and each material can be used by any geometry. So our gumdrops can use all 3, our jelly beans can use all 3, and our smarties can use all 3. And if we were to just take a look at this with a dome light, so let's just render this with a environment light over here, you can actually see our different suite assets, right? However, keep in mind that this is all being stored in a single asset. It is all being stored in this gumdrop asset. So we can now rename this to something like suites asset. And what this will do is when we save this to disk, it'll save a different asset, right? Save to disk. It'll take a moment and save it to disk. And once again, it'll save it in this location. And then if we use a reference node, we can bring in that asset. So let's go ahead and find it. So it'll be over here, underscore suites asset, right? And if we take this explore variance node, we can see that when we reference this in, it comes in as this single smartie over here. That's what it's defaulting to. But we can explore which variants are within it, and it expands it out. Alternatively, we can just set which variant we want. We can right-click on this asset, and at the top over here, you'll see that there's a geo variant list and a material variant list. We can easily choose, say, the gumdrop variant, and then of that gumdrop variant, change it to the gummy material variant, and you'll see that it adds these set variant nodes. So it's doing all of that for us. But if this was a more complicated asset, for example, an entire car with different car materials and interior materials for, say, the car seats and the dashboard, then you can see how this could be incredibly powerful. You could have a single car asset that gets brought in, and then you just set the variant, which changes the entire car material, as well as all of the interior details of it. So in this situation, we have 3 variants, and each variant has access to every material. But there are ways of making it so that each one of these geometries only has access to one material. And that's what this one over here is showing. So as you can see over here, this geometry is only getting one component material. This one is getting one component material, and this one is getting one component material. And then we're adding it to that component geometry variance node, and then we're outputting it, right? So this is a slightly different case. If we take a look at what this allows when we use an explore variance, you'll notice that we don't have as many options. So let's just say explore variance, reduce this, and let's also set this to nested variance because we have variance within variance. And you can see that we only have one material per geometry. So if we were to right click over here and choose a different geometry variant, the material is also linked to that variant, right? And this means that you can also get pretty complicated with the way that you set up your assets. For example, in this case, we're assigning 2 materials to the jelly bean, and we're even assigning a light to this gumdrop, right? So we're just merging in a light with this gumdrop. So we're doing a bunch of weird things over here. And then once we convert this to a single asset, what we can do is just explore our variants. And what you'll notice is that we end up with quite a complex set of variants. So reduce that spacing, and then we just drag over this dome light. As you can see, we have 2 materials for the jelly beans. We have a single material for that one over there, a single material for that one over there. But what's kind of weird is that this one also has a light underneath it, right? So you can see that one's extra bright underneath. That's because the gumdrop has a light merged in with it as a variant. So you can do all sorts of strange things with variants, but the base idea is just this one over here. Right? You just have a geometry, you have a material, you add it to a component material, that goes into this single component builder, and then you output it, right? So you output that out, and you can add things like variants. And over here, we just have the different examples that I showed. So we have a particular asset being brought in with a reference node. We explore its variance just using explore variance with a 0.1 spacing. That just gives us that. Alternatively, we can explore them as nested variants when we have variants which are specific to a particular variant. And what I mean by that is just that each one of these has a material that is specific to it. So that's actually a nested variant. Inside of each variant, they each have their own material. So it's nested. So we just take that nested variance. And over here, we just show that you can set a particular variant like that. So that goes over component building. This might have seemed quite complicated, but that's basically all you need to know for ever building any sort of asset inside of Solaris. And you can come back to this file and just use it as reference whenever you need to build your own assets. And hopefully this acts as a useful resource for you. In the next part, we're going to be looking at how to actually bring in these assets and use them in our scene and populate our scene with assets. So that's where we're going to start looking at things like instancing and all of those sorts of things. So I'll see you in the next part. Okay, so once we have an asset, oftentimes we want to take that asset and populate our scene with it, right? Now, what we can do is we can look at layout nodes and we can look at instancing. So instancing is this idea of taking an asset and only loading it once, but then copying it to a bunch of points. So we're instancing it. And the idea is that you're only holding one of those in memory, and the rest of them are just referencing that single one in memory. What that allows is for very complex scene building without a large hit to your hardware performance. So just keep that in mind, right? Instancing is when we take an asset, we load a single version of it, and then we copy it to a bunch of different points. Now, each one of those points can vary in certain ways. For example, if you're using the normal direction, so on a table like this, every normal direction would be pointing directly up. Let's say I vary that, so they point slightly in different directions, and then I copy some asset to all of those, then that asset can point in the direction of those normals, right? So that's something that we can do. We can also do things like scaling. So perhaps one copy is smaller than another copy. So instancing allows for you to take some particular attributes or traits and apply it to an instance, right? Now, in Houdini, there's 2 ways of doing this at the Solaris level. We have the layout node and we have the instancer node. Now, the layout node is kind of the simpler way of doing things. You build your assets, you bring it into an asset gallery, and from there you can just like place your assets wherever you want. The added benefit of using the instancer node, however, is that I find I have a lot more control and it feels more intuitive for me. But that's because I'm a Houdini artist, and so a lot of the workflow stuff makes a lot of sense to me. If you're not a Houdini artist, you can do pretty much the same thing with the layout node. It's just going to take a little bit more tweaking and it might be a bit more finicky. But if you are a Houdini artist, I implore you to kind of take a dive into the instance node and figure out how it works, it allows for some really, really cool stuff. So I'm going to explain those two concepts to you now. Let's get straight into it. Alright, so in the previous part, we just looked at how to actually build assets that we can use within Solaris, right? So we can now import USD assets and they can have variants and all sorts of things. Now, the next thing that I want to show you is the layout node. So over here, if I just switch on my Karma render view, I can just show you what we have. We just have this over here. And if I use the switch node, I can just show you the two other things that we have set up. So we just have this grass being scattered over here. And we also have these Smarties being scattered over here. So I'm just going to show you how to do these three setups, how to create them. And so let's start with this first one, right? So this one over here, what we are doing is we're bringing in a grid. So we're just creating a grid at this level. So at the Solaris level, we're creating a grid. Then we're using a layout node. And this layout node allows us to place gumdrops, right? We've placed gumdrops over there. This one over here allows us to place lollipops. And then this one over here just changes the variant for some particular lollipop. So if I want to change a particular lollipop, I can just choose from the ones that are over here. So let's just say that I want to affect this one over here, right? So I can just drag this over and then change the variant. And you can see that it's changed it to a different lollipop. So that one is a transparent lollipop, but we'll get back to that shortly. Okay. So let's just say we have this grid and we want to populate it with some assets. What we can use is the layout node. So I'm going to go down here to the side and just drop a new grid. So one over here. And I'm just going to shrink it down, so 0.1. And then we can go ahead and use a layout node. Now, the layout node allows us to place particular assets on a geometry. Currently, we don't have any assets to use, and so we need to bring them in. To bring in assets, let's add a new tab over here. So next to your scene graph tree, you have the scene graph details and the scene graph layers. Let's add a new pane, and we'll go over to Solaris and just use the layout asset gallery. Now, when I open that, you'll see that I have these over here that are already set up, right? Now, these are assets that we've brought in. Remember how we rendered a thumbnail for our various assets? This is where they start to show up, right? So you can link up a thumbnail to a particular asset and then add it to an asset library. So I'm going to create a new asset library just to show you how to do that. All you have to do is say create new asset database file. You can add it to some new folder, for example, asset_galleries. And in here, you can just call this asset gallery _database. And what it'll do is create a new asset gallery database for you, and you can start adding assets to it. And anytime you want to use the layout node, you can just load that particular asset gallery by going over here and just saying open asset database file, and you can choose some particular file. To add an asset, just go over here to this little teddy bear. And what you need is a label, a file, and its thumbnail. You don't have to have a thumbnail, but it is optional. So we can go ahead and choose a particular file. Let's go ahead and use that gumdrop asset that we created in the last part, gumdropasset.usd, and we can just name this gumdrop, right? So that's the name that will appear for us. And then we just have to load its thumbnail. So over there, thumbnail.png, and then we say, okay. Now you can see it shows up in our gallery, right? And I can still load my existing gallery if I go over here and open my other database file. Right over here, I have this one, or I can open that one that I just created, right? So inside of asset galleries, this one over here, just like that. Now what I can do is just drag this gumdrop over into the layout node, right? So the layout node has the section which sort of matches. You can see they both have this little teddy bear and stuff. But once I have it in here, I can start placing things into my scene. So I can use the place option over here, and I just need to switch to my transform handles. So select something from here, switch on your transform handles, and this will allow us to place gumdrops. You can click and drag to adjust the size, but you can just place as many gumdrops as you want, right? So you can just place them wherever you want them. And this is a pretty useful way of just placing assets. And you can have different assets. So if you have 3 different assets in here, you can just like cycle between them or select different ones. And you can even place, assets on top of assets, things like that, right? So something like that. Additionally, you can even fill particular areas with them. So if I activate the fill mode over here, and then I just change this to the lasso mode, I can go ahead and select an area. Now you'll notice it only placed 1, but that's because there are some scatter options. You can see that there's a coverage option, there's a min radius, max radius. If I increase this coverage scale to like 1000, and then I drag, you'll see that it really fills out that area. I can reduce it to like 100, something like that, or just a particular amount that seems to fit. So by 500. And then of course you can give it a minimum and maximum radius. So a minimum radius of like 0.5 will allow some small ones to be placed, right? So now I can populate an area with smaller assets. And just like that, I can actually drag over this dome light over here. So Alt, click and drag. And if I just set this to my Karma view, you can see that we have these weird looking gumdrops placed into our scene. But what we can also do is we can add a separate layout node. And that's exactly what I've done over here, right? So I have one for gumdrops and then one for lollipops. And we can go ahead and add another layout node and do exactly that. So just switch your Houdini viewport back to the default. Let's use another layout node. So this layout node over here, I'm actually going to use a different gallery. So I'm going to select this one. And over here, I'm just going to change my gallery. So open asset database and just use this one over here. And let's drag over the lollipop spiral, and the lollipop flat. And now I can just place them into my scene using the place tool. So right over here, I can just place one right over there. I can choose a different one. And a different one over here. Okay, so I have these 3 different lollipops, right? And if I go ahead and take a look at them in my Karma view, you'll see that I have these over here, right? And let me just switch on my dome light. So you can see I have some variation. Now let's say I'm not particularly happy with one of these lollipops. The downside of using the layout node is that by default, it will instance. Now instancing is incredibly powerful. What it does is it creates one version of an asset, and then from memory, it just creates references to that asset. So all of these gumdrops over here, these are all instanced. If I go to this layout node over here, and I expand my layout node, you'll see that all it contains is a single gumdrop. Even though there's a bunch of them scattered over here, there's only one gumdrop asset that it's referencing. And so that saves a lot of space in memory, because all it's doing is it's taking one asset and then just copying it a bunch of times, right? So it doesn't have to store all of those assets. However, in the case of our lollipops over here, maybe we don't want that, right? So if we go over to the options over here, you can see that the method is pointInstancer. If we change this to instanceable reference, then what that allows is for us to actually individually affect each one of those lollipops. So if I expand layout 2, you can see that I now have access to the various lollipops that make it up. The great thing about that is that I can change things like variants for each of these lollipops now. So let's just say that I don't like having 2 of the same spiral lollipops. I can right click on it and change the geometry to another round one, right? And just like that, I can now affect each one of these assets individually. So all I have to do is go over here, change it to instanceable reference, and that creates individual references as opposed to instances. Now, of course, it is preferable to use instances for as much as you can, but instanceable references are an option. Okay, so that's the layout node. I'm just going to delete that over there. And that's what we have on this left-hand side. 2 layout nodes, one for gumdrops, one for lollipops, set the variant, and then render it, right? So that's exactly that over there. Now, the other option that we have is to actually use an instancer node. And this is what I find myself using most of the time, because I generally just want to populate a scene and not have to place things manually. So this one is going to be a bit more confusing for somebody who doesn't use Houdini. But if you do use Houdini, then you'll kind of understand what I'm doing here. So I have this grid, and all I'm doing is I'm attaching a null. The reason I'm adding this null is so that it's easy to reference, right? So I can just reference this null and be like, this is my grid, use this. So I then go into my instancer node. And inside of my instancer node, all I'm doing, and I'm just going to hide my other objects, all I'm doing is that I'm finding that node, right? So I'm finding that geo node that I just created. And then I'm finding the primitive that I want from that node. So from geo in, I want the grid primitive. That's what I'm doing over here. So I'm bringing it in using a lop import node. Then I'm using this unpack USD, and I'm unpacking it to polygons. That just allows me to edit these polygons. If I take a look at the smooth wire shaded, over here, I don't actually have access to the primitives that make it up. I just have a packed USD object. But over here, I can now unpack it so that I have points and primitives. I can then subdivide it for more detail and then use an attribute paint. And if I attribute paint, I can then paint on things like masks, just like that. And then use a scatter and align node. Now the scatter and align node will allow me to scatter some points based on some criteria. And I can just increase the size of these so that you can see them more clearly. But as you can see, I've just scattered some points, right? These points are scattered based on this attribute that I painted over here. So you can see that only where I've painted do I have points. And this over here does some things for us, right? It generates orientations for us, so we can actually automatically rotate around the normal. We can have some randomization to the cone angle. And what that means is that when we copy things to these points, they'll pick up these randomizations. They'll have a slightly random angle and a slightly random tilt. Cool. So if we go up a level to our instancer, we can then reference in some sort of asset. So in this case, I'm just referencing in this grass asset. And then all I have to do is plug that into the second input of the instancer, and it instances it to all of those points, right? So if I take a look at this one, you can see that I'm just rendering out these pieces of grass, right? So I've scattered them, and they all have sort of random orientations and things like that. And you can do all sorts of different controls with this. For example, you can see that some of them are different sizes. That one over there is bigger than that one over there. That's driven by certain attributes within here. So things like p-scale will control the size. So I have p-scale, I have an orient attribute, and all of these things can actually adjust the thing that you're copying to these points. So the scale is adjusted by the p-scale. Okay, great. So that's one way of instancing. Now what happens if you want to instance but randomly choose from variants within an asset? We can do that as well. So over here, I have this instancer node. So in this one, I'm still doing the same thing where I'm fetching my grid, I'm unpacking it, I'm subdividing it, and then painting on a mask, and then I'm scattering and aligning, right? So all of that's the same. However, what I'm doing now is I'm fetching my Smarties, so these over here, and these actually have a bunch of variants in them. If I drop an explore variants node, you can see how many variants are within it. Let's just do an explore variants node and decrease the spacing to 0.1. You can see I have a whole lot of variations, right? So there's a whole bunch of variants within the single Smartie asset. The way that I use it in an instancer is I explore those variants with this node set to duplicate. So all it's doing is it's duplicating all of my variants onto the same location. And then I'm creating a collection of those variants. And then I'm using it in the instancer. So I'll show you this workflow quickly. So we have this reference node, which brings in a particular asset. And then we use that explore variants node. With this explore variants, you just leave it at duplicate variants. And then you use a collection node. Now a collection is just taking all of the inputs, or at least whichever ones we choose, and assigning them to something called a collection. A collection is almost like a group, but it's just a selection of particular primitives. So we can change this collection name to something like Smarties underscore collection. And the primitives that we want, that's not it. So we want to go over here to our explore variants, Smarties, and we just want to drag this over. And then we want to say /**. So everything inside of this primitive is going to be what gets added to this collection, right? So now everything inside of explore variants 2, inside of Smarties, is now being added to the Smarties collection. So that means that all of these over here are all being added to a collection. Now, this is where you want to plug it into your instancer. And so we take this and we plug it into our instancer. However, on the instancer node, you're going to have to choose which collection you want. So over here, you'll see that we have the prototype primitives. We're going to have to choose which one we want. If you use the dropdown, you can see right at the bottom, we have collection, Smarties underscore collection. So we select that. The only other thing that we have to set is this only copy specified prototype primitives. We don't want only specific primitives. We want everything in that collection. So by default, it's enabled. You just need to disable that, and then this will work. It'll copy a Smartie to each and every point that you have. And again, if we render that, we can just switch to that one. And just like that, we have our Smarties being instanced. And again, remember, these are instances, so we can go pretty crazy with the amount of Smarties that we have over here. For example, I can go in here, and let's remove this attribute mask, make it not use that mask attribute, and then push up this density to like 5,000, right? So loads and loads and loads of points. And then let's see what that does for us. As you can see, we have a whole bunch of these Smarties being scattered. So you can see if we set a render of that, we just have a whole lot of Smarties being instanced, right? And so we have a lot of control when we start using things like instances along with things like our layout node. So we can mix the two of those together if we wanted and end up with some really cool results. Right? So things like that. And so that's just a brief look at how we can actually use instances and layout nodes. And just so you know, the instancer node always works with instances. So just like how we had instances being created by our layout node, that's the same thing that happens with our instancer node. Of course, you can change the method as well. I wouldn't necessarily recommend it because you do want the added benefit of just instancing. So that's it for this part. Once again, all of these files are included so that you can go back and take a look at them and understand how they work. So I'll see you in the next part. All right, so thus far, we've just been using Vex-based shaders. When I say a Vex-based shader, I'm talking about shaders that are built with Houdini's code called Vex, right? That's the code that all of the shaders inside of Houdini are built with. So we can actually render our Vex-based shaders, and that's the principal shader, with Karma or Mantra, right? There'll be no issues if you render your principal shaders out in Karma or Mantra, but let's say that we want to render it in Arnold. If we try and render our Vex-based shaders in Arnold, we're going to have an issue. They're not going to work because the code is specific to Houdini and Houdini's renderers. So this is where MaterialX comes into the picture. MaterialX is like the USD of materials, right? It's this idea that we can have a material that's universal. So we make a material in Houdini, then we can load it into Arnold, we can load it into Redshift, we can load it into V-Ray, and we can render it out in any of those 3D renderers and end up with a very similar looking material across any platform. Another thing to keep in mind is that even Houdini's Karma doesn't use Vex-based shaders. And when I say this, I mean the XPU version of Karma. So Karma has a CPU version and an XPU version. The CPU version can use Vex-based shaders. The XPU version cannot. So you will get like a preview shader, but things won't work. You won't have things like displacement, subsurface scattering, things will break. So avoid using Vex-based shaders if you're using Karma XPU. If you are going to be using XPU, then go ahead and use MaterialX with it. MaterialX is pretty great, right? I'll show you how to build MaterialX shaders and all of that. So let's get straight into that. Right, for this part, we're going to begin looking at MaterialX. So MaterialX is a shader which is accepted by many different renderers. So you can take a MaterialX material that you have created and you can render it in different render engines. So much like how USD can be opened in various DCC packages, MaterialX can be rendered by different renderers. So when we combine the two, we end up with a workflow that allows us to open our files and render them in many different engines and software packages. So we're going to go ahead and just texture this door. So over here, there's just a biscuit door and it's got a little door handle. Over here, you can see that we have the biscuit door and doorknob. Those are groups. You can also use names. So these are just two ways of assigning materials to particular things. I've shown you before that the name attribute over here separates our geometry. Groups actually don't separate our geometry, but we can still reference them. So that's useful if we don't necessarily want to treat the door and the door handle or the doorknob as two separate pieces of geometry, but we still want to be able to assign materials to them separately. So you can do that if you'd like, but I'm using the name attribute. Okay, so let's go to the stage level. At the stage level, I already have a bunch of things set up. I have my door being brought in over here, and then we're assigning some materials to it, right? So let's take a look at what this material looks like. So if you open this up, you'll see that we have two subnetworks. Now, the reason that we have these subnetworks is that there's actually a node that generates these networks for us. If we tab and type USD subnet, you'll see that there's this USD MaterialX subnet. And if we place that, we can dive inside of it and it has these things over here. So why would you want to do that? Apart from things being a lot neater when you do it this way, there's an added benefit. So when you tab in this menu, you'll see that we have loads and loads and loads and loads of options, right? And if I want to do something like an add, you can see that I have add attribute, add constant, all of these things. And over here I have MaterialX add. Now MaterialX actually comes with its own set of nodes, and they don't behave well with Vex nodes. So if I throw in a Vex node and then combine it with a MaterialX node, there's going to be some issues, especially if I'm rendering with Karma. So Karma XPU, the one that uses your GPU and CPU, that one doesn't actually accept Vex shaders. So you can't use something like a principled shader in Karma XPU. And so when we start adding Vex nodes into our MaterialX shaders, that ends up breaking our MaterialX shaders when we try to use them in either other software packages or in Karma XPU, because those are nodes that are specific to Houdini. MaterialX nodes aren't specific to Houdini, so they can be opened up in other software packages. So the benefit of using a MaterialX subnet is that when we do this MaterialX subnet and we dive inside and then we press tab, you'll notice that we have very few nodes. That's because it actually filters out all of those extra nodes. So now all of our nodes are MaterialX. So if I type add, we only get the MaterialX add, right? So that's the added benefit. You never end up with mixed shaders where you do something like this and you end up with this add node. In a MaterialX subnet, the only thing that you have access to are the MaterialX nodes. So now that we understand that, let's go inside of these over here and just take a look at, firstly, a very basic MaterialX material, and then a more complex MaterialX material. So over here, we just have a MaterialX standard surface. Now the MaterialX standard surface is much like the principled shader in Vex. It has all of the same options, things for like coat, and we have specular. So it's just a very useful standard surface shader. It's pretty general, right? And over here, I'm just using some noises and things to generate a bit of a pattern on our doorknob. You can see that it's generating this sort of wally pattern on the doorknob. And that's just to show you that we can use noises inside of MaterialX. Now, I'm going to show you how to build one from scratch. So we'll start with a USD subnet, so USD MaterialX subnet, and we'll call this door. Right, so over here I have door underscore MTLX. I'm just going to replicate what's in here. So the first thing that I'm going to do is delete this MTLX surface. This is actually for if you need to combine various shaders to build a surface, but we don't need to do that. So we can remove that surface. And we don't even need this input, right? So this is all we actually need. We have these two over here for displacement and one for the surface. So all we have to do from here is just type a standard surface. So you see MTLX standard surface, and you can plug that into the output surface. Now I'm going to go up a level, and instead of using the pre-made one that I have over here, I'm going to assign my new one so that I can go through it with you and build the entire thing from scratch. So we'll autofill, and over here we have door. I'll assign it to the biscuit door. Right, so /door/biscuit door. And what you'll see is that it actually overrides. So the lowest assignment in this over here is the one that actually gets evaluated. So if you have conflicts, the last one that you assign is the one that gets used. So that's why it overwrites. And if I just set my display flag over here and then try to render, you'll see that it's just a plain white door. Okay, so we can go inside of here and work on this door material. The first thing that we want is a image node. MTLX image is how we bring in textures. So over here, you'll see that we have a signature. So this is generally where you choose color or float. So color for something like your base color, or float for something like a roughness map, which is only between 0 and 1. So go over here to the file name, and inside of main, under textures, you'll see that we have biscuit door. Inside of here, we have base color, height, normal, OpenGL, and roughness. We'll choose base color, and then just plug that into the base color. So it's really as simple as that, right? You just take a MaterialX image, plug it into whichever one of these you need, and then it applies it. So let's go ahead and continue on. MaterialX image. This one we'll choose roughness. So just choose roughness, and we'll change this to float because this is a black and white image rather than a color image. We'll just plug this into our specular roughness right over there. You'll see that that will make our door a lot more rough. So now we're going to do a normal map, and this one's going to be a bit different. So we're going to do MTLX image as we've done before, and this time we're going to choose our normal map. However, we don't actually want it as a color, we want it as a vector 3. So if we think about it, we're not reading this as a color, right? In the case of this over here, where we're setting our base color, we're not actually using this as a color. We're using this as 3 separate vectors to drive our normal displacement. So we change it to vector 3. Then we go ahead and use an MTLX normal map. So the normal map node over here, we'll take this and conform it to a normal map standard. So we plug that in there, and then that can go into your normals. When you do that, you'll immediately see that we now have these nice normals on the door. You can see that it's not actually displacement. If we zoom in, you can see there's no displacement of the actual surface. It's just a normal map, so it's affecting how the light hits this door. Okay, so we have this, but we would like some actual displacement. So all we have to do is once again do an MTLX image. And this over here, we can go ahead and choose our height, right? And this again is going to be a float because it's a black and white image, and then we plug that into displacement and the whole thing will get blown out because we have a scale on the displacement that we need to adjust. So we'll do 0.01, and as you can see, there is now actual geometry displacement of our door. Now, something that you can do, and this is going to be particularly useful if you're working with things like Quixel assets, is use a remap range, so MTLX remap. It's not going to actually work on this because the way that this one's been set up is meant to have its displacement in the range that it comes in. But sometimes you might have a range of 0 to 1 and you want to change it. So you can use this. You can go to minus 0.5 and 0.5. And what that will do is it'll just remap the range. You can also use a color correct node. I've noticed that this is also something that pops up sometimes with Quixel Megascan assets and things. This over here, what you would want to do is actually reduce the gain by 0.75. It's a bit of a strange thing, and I'm not exactly sure why you want to do that. But just keep this in mind. This is something that I've done a couple of times with MaterialX materials when I need their displacement to behave correctly. So you'll use this plus this, or you'll use maybe just the remap. But these two over here just become useful for making sure that your displacement works correctly. This gain over here is the same as a color offset. So I think on the Vex texture nodes, I think they have a color offset. And I think also on Redshift texture nodes, they have a color offset. This is the equivalent. You can just reduce the gain. So that over there works pretty nicely. Okay, so let's go ahead and also just plug our base color into our subsurface. So over here, you can see that we have our subsurface color and radiance. Let's go ahead and do that. So to subsurface color and subsurface radiance, we'll just take our base color, that, and then push up our subsurf and then reduce the scale to 0.01, just so that there's a very slight subsurf to our door, right? You can reduce that further if you want. So 0.5, something like that. Alternatively, this subsurface over here actually kind of disables your normal map. So if I switch off displacement for a second, you can see that the normal map doesn't really show up. It doesn't do anything anymore. That's because subsurface actually overrides normal maps. So if we reduce the subsurf, you'll see that our normal map returns. So you can actually balance it. So choosing how much you want your subsurface to show and how much you want your normal map to appear. But it's no biggie if we also have displacement, because that kind of fixes that issue for us. Okay, so there we go. We have our biscuit door and it's looking pretty good. So that's all you have to do, right? All of these things over here are just MaterialX image nodes. The only catch over here is to use a MaterialX normal map. But really, it's pretty straightforward. And I'll be showing you how to bind in particular attributes. So if you have something like a color attribute that you want to bind in, or a mask, I'll show you how to do that. You can also do things like color mixes. There's a whole bunch of MTLX nodes in here. You'll see that some of them have this little SideFX logo next to them. That means that these are specific to SideFX. How it's working is that MaterialX is under development. And so oftentimes there are nodes that don't really exist within the MaterialX context. So what SideFX has done is that they've created their own nodes which conform to MaterialX standards that can do the kind of things that you might need them to do. For example, the ramp node over here, you can see that we have a color ramp. It doesn't exist in MaterialX, but Houdini has made one. So you won't find this node existing in some other 3D packages because it is Houdini specific, but it does still write out as correct MaterialX code. So if that makes sense. All right, so that's all we've done with the door MaterialX. If I remove my door over here, you'll see that the other one looks pretty much the same, maybe a bit more subsurf or whatever, but it's basically the same thing that I just showed you. Okay, so over here, we also have this doorknob MaterialX. So I'm also going to recreate that one. Let's just go ahead and create a USD subnet. We'll just call this doorknob. And inside of here, we'll once again delete the surface and inputs, and then we can just go ahead and use a standard surface. Okay, so let's plug that standard surface in, and let's go assign this to our doorknob. So our doorknob over here will autofill materials. We now have one for doorknob. We'll just overwrite /door/doorknob. And as you can see, it's now turned white. So now it's using that new material that we just placed. So if we go to the doorknob over here, we can go ahead and use a noise. So let's go ahead and use a Wally noise. And we have a 3D noise over here. If we plug this into our base color, and I'm just going to start with base color because it's easy to see, you'll notice that it's not really doing anything. The whole thing's just kind of turning gray. And the reason is because we need a position value. So all noises are driven by their position in space. So that needs some sort of value to drive it. What we can do is we can drop a position node, MTLX position, and plug that into the position. Now you still won't notice anything, and that's because the noise pattern is too big. So we're using the object space at the moment. You can use world space or you can use model space. So object space, as far as I know, will stick to an object if it's moving. World space won't. So world space is just fetching this thing's position in the world's space. So if it moves inside of world space, so will your noise. Now we can go ahead and use a multiply node, so MTLX multiply. And with this node, you can adjust the second input over here. So middle mouse on the name of the parameter and just push it up, all the way up, and you'll start to notice a bit of a noise pattern forming, right? So we can push that up even further, and there you go. You can now start to see that Wally noise. And so you can just take that and plug that into your roughness rather, so specular roughness. And then on the actual color over here, we can give this a metalness, and then also change its color a bit. So as you can see, you end up with something like that. So we can also use a remap, things like this, to adjust this range. We know it's between 0 and 1, and so we can just change it to something else like 0.25 to 0.5, right? So a lower range of values, it gives us a slightly roughed up material. So we can use noises like this inside of MaterialX, and they'll work perfectly fine. Right? I mean, you can even use this for something like displacement if you really want to, and then just reduce that scale. So you can see all of these types of things actually work inside of MaterialX. So MaterialX can be used in many different renderers. I will include a list over here at the moment. I can't recall them off the top of my head, so I'll just go do some research for you and throw them on the screen now. But these are the ones that will use MaterialX. I've tried this with Unreal as well. You can bring a USD asset into Unreal with MaterialX shaders, and it will actually read it. So you can build all of your assets through things like component builders, and you can build them into USD scenes, and you can send them off into Unreal. So all of those types of things are really cool, right? It allows incredible collaborative workflows, not just between people, but between software packages. So this is just something to keep in mind. We're going to be using MaterialX for the rest of this tutorial series. So this is just a reference on how to use it. So if you ever need to come back, you can open up this file and check it out. So yeah, let's move on to the next part. Inside of Houdini, we often work with attributes, and that's because Houdini is very much a data flow type of software, right? It's very important to have your information flowing from one node to the next, to the next, to the next. However, when we move from the object level to the LOP level, or the staged network, then we sometimes lose that connection, right? There's some attributes that we might not be able to find, or we might not know how to use them. And that's something that's been tricky in the past, bringing certain attributes in and using them in shaders and things like that. There's always been a bit of nuance to it and a bit of knowledge that you need to actually be able to do that. So I'm going to explain to you in this part how we can take our attributes from the object level and bring them in and use them. But more than that, I'm going to be explaining what primvars are. Now, primvars are all of the defining features that exist on a primitive. So a primitive might have something like normals, it might have UVs, it might have point positions, right? All of those things. Those are all primvars. And those are just variables that exist on a primitive that define it, right? And so we can have custom primvars. So I'm going to be showing you how to use that and how to bring them into a MaterialX shader. So let's get straight into that. So in this one, we have 7_primvars, right? That's the file if you want to open it up. And in here, all we have is this sphere. We're giving it a blue color, and then we're adding a attribute mask, right? So this mask over here, you won't be able to see it, but it's just an attribute that ranges between 0 and 1. If we click over here, you can see that that's the mask. Black is 0, red is a value of 1, and then there's a range to anything in between. So we're going to be using that mask inside of our stage level, but just so you know, these two are saved as attributes. CD is your color, mask is just a random mask attribute that we've created. So if we go over to the stage level, we have our sphere, right? It's being brought in. Now, if we scroll down, you'll see that we have attributes that can be brought in, right? Now, these attributes over here, it says bring in everything except these things. So you may want to see where those attributes are, and we can go find them. If we extend this up over here, we can go ahead and click on our mesh over here. And what that'll do is it'll show us all of the different primvars. Now, a primvar is actually what we would call an attribute in Houdini. Primvars are just pieces of information that are held on a geometry or a primitive, right? So on a primitive, there are some variables that can change, and those are known as primvars. That can be anything like your position in space, right? It can be the material binding. It can be normals, UVs. All of those things need to be stored somewhere on this geometry, and they are stored as primvars. So if we just drag this over, we can actually see all of the different primvars that make this up. Let's just scroll down to where it starts to show as primvars. You will see over here we have primvars mask. That's our mask that's being brought in. So that's that attribute that we created, and it's being brought in over here. However, you won't find CD anywhere, right? The color attribute. It won't show up anywhere over here. And that's because there are certain attributes that get brought in that actually get changed to a USD specific name. CD gets changed to display color. So this one over here, display color, that's actually your CD attribute. And I've included a little cheat sheet over here so that you can see which ones get changed to what. And this is just because in various software packages, you have these particular things, such as color, normals, positions, UVs, and velocity. And lots of 3D packages use those, right? They're not like custom attributes. So to make sure everything works correctly between software packages, what happens is USD conforms it to these names. So you can see that CD becomes display color, your normals become normals, position becomes points, UV becomes ST, and velocity becomes velocities. So that's just a little thing that you can use for reference, but all that means is that these things over here get renamed to these primvars. Any custom attribute keeps its name, like that mask over there. So how can we use that, right? How can we use primvars? There's many ways you can use it, but the important way that I want to show you is for your materials. So if we dive inside this material library and inside of this sphere material, you'll see that I have this MaterialX mix, and it's just mixing between two colors and then outputting a color. So if I switch on my render over here, you can see that we have this sphere and it's mixing between two colors being controlled by this MaterialX mix and a geometry property value. Now I'm going to rebuild this so you know exactly what's going on. So let's go ahead and create a new USD subnet, so MaterialX subnet, and we'll just call this sphere. And upper level, I'll just fill these materials and assign it to /sphere. /mesh underscore 0. Okay, so it'll overwrite, and now we just have this. So we can go inside, once again delete the surface and inputs, and then go ahead and create a standard surface. So MaterialX standard surface, plug that into the surface. Now, if we want to bring in attributes, right, we can use a geometry property value. So over here, MaterialX geometry property value. What this will do is it'll look for a particular primvar. So all we have to do is take the name of a particular primvar that we want and just put it in here. It's really that simple. So if I want something like my display color, I just put display color, and it is case sensitive. Then I can just switch this to a color because that's the type. And you can actually see what the type is over there. You can see that it is a color 3 float. So we can take that and plug that into your base color. And there we go. Our color is now being brought back in. If I go to my object level and I change this color over here to something like green, and then I go back up to my stage level, you'll see that it changes to green as well. All I'm doing over here is I'm fetching that particular primvar and assigning it to my base color. So what about custom attributes? Custom attributes are exactly the same. So once again, if I just use an MaterialX geometry property value right over here, you can tell it which primvar to look for. So I'll tell it to look for mask, and I'm just going to plug this into base color over here to see what it looks like, right? So it's just that. Now, of course, I can go ahead and use that for all sorts of things like mixing. So I can mix between two materials over here. So let's just mix between this base color. So we'll use this as the mix. So now you can see that it's mixing between our green CD color or display color and this background color. So I can just change this to whatever I want. And actually, just to help you kind of understand how you would use something like this, it might be for something like this, right? Where let's just say the brown is like a dirt texture, and then the green is like a grass texture. That's where you might want to use something like this. So you can use a particular primvar to drive a mix between these two. And something cool that you can do inside of MaterialX is that if you want to debug a particular node and see what kind of value it's bringing in, all you have to do is click on the node and then press X. What it'll do is it'll drop this visualize node, and it'll visualize whichever node you had selected when you pressed X. So just to show you this, if I click on this one over here where I'm just getting my display color and press X, you can see that's the color being brought in. So if you're familiar with Houdini, this would be something like this little debug over here where you click on that. But that doesn't do anything in MaterialX. All you have to use is just that X, and it visualizes something for you, and you can just see exactly what it is. Okay, so that's all we're really going to look at for this, and we can go ahead and move on to the next part. Oftentimes you might have an asset that's already been created for you, and you bring it into your scene, right? So say you're working in a studio and somebody has given you an asset. However, maybe the material is not exactly how you'd like it. What you can do inside of Houdini and inside of Solaris is that you can edit that material directly. So by using a material network edit node, we can load a material that's already been built and we can edit it in a non-destructive way. So I'm going to show you how to do that now using that material network edit node. For this part, we're going to be looking at material edits. Now for material edits, the idea is that we can take somebody's shader that's already been created for us. We can go ahead and we can edit it ourselves and make any necessary changes in a non-destructive way. So that means that we can always just disable the particular node where we made the edits, and it'll just return to the default that the person has given us. So let's go ahead and open up this file over here where we have 8_material_edits. And what you'll see at the stage level is just this cake base. Now, a few things to note about this cake base. It's actually a high resolution geometry, but in the viewport, it's showing as this proxy geometry. You can go over here to these sunglasses, and over here, you can actually switch between some options. So this is your preview. So if you click preview, it will switch proxy to what's active. If you switch to final render, it'll switch to the final quality that will be used at render time. Now, this is actually something that goes back to our component building thing that we did. When we are using the component builder, so I'll just show you that, component builder. Remember how in our component geometry, we had the option over here when we use external SOP to choose a render geometry, a proxy geometry, and a sim proxy. That's all we're doing over here, right? So that's what it allows. It'll automatically detect proxy or final render. This is just nice. Obviously, you'd imagine that as you have higher geometry load in your scene will slow down. So you might want to start using proxies if your scene gets a bit heavy. So again, just preview mode like that. Okay, so let's go ahead and take a look at our material that we want to edit, right? So if I take a look at this as a Karma render, and I'm just going to remove this edit node over here, you can see that we have like this chocolate cake, right? So it's just a chocolate cake base, and we can do whatever we want with this chocolate cake. Now you may feel stuck at this point because, you know, someone may have created this asset for you and you don't really have control over what's going on inside of it. Very simply, we can go over to this cake base over here under the materials, and we can edit that. So let's use a material edit. So edit material network, plug that in between, and all we have to do is drag over that cake base material and then say load. Now it won't change anything, but if we double click on this node, it'll now behave like a material library node. So open it up, and this is everything that went into creating this particular material. So over here, you can see that we have that same displacement thing that we had before. So let me just reorganize this so it's easy to see. So we have the same thing that we had before, right? We have a standard surface coming into the top. We have a displacement coming in over here, but we also have this down here, which is a preview shader. So I'll show you that shortly. But for now, let's just focus on this over here. If you click on this MaterialX standard surface, you'll notice that everything is grayed out, right? And that's because when we write this to USD, right? So to disk, in our USD file, only the things that are being changed need to be tracked, right? Or else our USD files will kind of get heavy. Imagine if we have a material and then every single time we reference that material, it saves all of this information. That's not what we want. What we want is for it to reference the material once, and then anytime a change is made, only adjust that particular thing, right? So don't like recreate the entire shader, still reference the original, but then make these edits that we're asking for. So let's just see what happens if I activate base color, and then I go over to subsurf and I activate subsurf, and I switch off subsurf. So I've switched off subsurf, and all I'm using is base color. And this base color can now be adjusted, right? So maybe it's something like a vanilla cake. Something like that, right? So you can see that I'm now actually making changes to the material. But this is non-destructive. So if I go up a level, back to my cake, you can see I still have that original material, and then I'm just making a change over here. So that means that I could easily bypass this node and end up with the exact same thing that I started with. But I now have access to everything inside of here, and I can make as many changes as I want. For example, I could also take this base color and I could change the subsurface color. So let's push the subsurf back up and adjust these two. Now you'll notice that those are grayed out, and that's because they're being fed in this over here. So this MaterialX image is being fed into the subsurf, so all we have to do is break that link, and then we can now adjust these two individually, right? So now I can just change this to whatever I want. So something like a red velvet, so I make that red, just like that. So as you can see, it's really simple to just edit the materials that you have over here. And you can just go in and make whatever changes you want, and then very easily bypass it if you want to go back to the original, or keep it like this, right? So that's all I'm doing in that edit material down there that I disconnected. But the idea is to just override particular things within an existing material and then have that be written to disk. Okay, so the only other thing that I want to mention is just this over here. This surface preview, right? So we have this USD preview surface. Now, what you'll see over here is that there's three shaders being plugged into this collect node. We have one for displacement, we have one that's our actual standard surface for MaterialX, but then we have a USD preview surface. And this is not really going to apply for when we're working inside of Houdini, but if we're working in any location where this isn't recognized, then it'll default to using this USD preview surface. And we can actually make it so that our Houdini viewport doesn't actually use the MaterialX preview that gets generated, and it can use this one instead. But I believe that's an environment variable that you'd have to change. And that just allows for complex MaterialX shaders to be built that maybe don't display correctly in the viewport. And then you can just use the preview surface to display them in the viewport. So that's just something to keep in mind if you want to dive deeper into that. I think the best thing to search is just Houdini USD preview surface, and you should be able to find some resources from there. Okay, so that brings us to the end of the material edits part. Let's move on from here. Oftentimes, you might want to bring in simulations into your LOP network, right? Now, this is going to be particularly useful for anyone who is working with simulations inside of Houdini. So any sort of effects artists might find this useful. But there are a couple of things that you need to keep in mind when working with time-based effects inside of USD and Solaris. And so I'm going to be showing you how to first optimize your simulations, how to export them, and a couple of little things to keep in mind for when you want to render them or save them out. So let's get into that. In this file, we have some simulation data. So if you open 9_simulations, we have this over here. Importing simulations into USD is going to be incredibly important, especially if you're working as an effects artist and you want to bring in some time-based simulation data. So as you can see, I have two networks over here. I just have the snow and I have the rain, or the other way around rather. So snow is falling slowly and gathering. The rain is falling fast and splashing. Okay, so these are just using a collider of this house geometry, which is being brought in from the stage level. So it's just this little house over here. I'm unpacking it to its geometry, turning it into a collider over here, then using that collider in these two networks over here, so the snow and the rain. Now, if we want to bring that into our network, so our USD LAPnet, then we can go over here to stage, and it's quite simple. So all we have to do is go over here with a SOP import. So again, SOP import, but this time we're just going to be bringing in a simulation. So we go over here and we can choose something like rain. So over here we have our rain being brought in, and this one over here you can just call rain. And a useful thing to do is put into /sim or /simulations, whatever you want, right? Just so that we have an easy way to access it over here. And then all we have to do is bring it in with that house. So let's actually take that house that we sublayered in and see what it looks like with the rain. So now we have the house, and it'll take a second to load. Let's also drop a dome light, and this dome light can just take some random light. So we'll just take whatever we have over here in general assets, HDRI, we'll take this one. Okay, so let's take a look at the render and what we have. Okay, so it doesn't really look like much, right? We can see that we have our particles being brought in. And if I just hide the house for a second, you can see that it's just these tiny particles, and they don't really look like anything as of yet. The reason is we don't have things like motion blur, and they also don't have a material. You can very easily apply a material with a material library. So I'll just add one over here. And inside of this material library, we just have to create an MaterialX standard surface. So I'm just going to create one at this level because we don't need all of the complexity that we usually do. I'll just minimize it, call it rain material, and then just give it some transmission, right? So like glass or water. And then over here, just assign it to the geometry. We'll say auto for materials, drag over our rain simulation, just like that. And now you can see our particles now have transmission to them, right? So each little raindrop now renders as a transmissive sphere. Now, why is it rendering as a sphere, and what defines the size of that sphere? That all gets brought in by our attributes. So if we go to this simulation over here, you can see that at the end, when I'm outputting my rain, I have a few attributes on it. I have P, P scale, and V. Now, P is just your position. P scale is going to be the size of each point. And then velocity over here, that's your V. If we want to take a look at velocity, we can using point trails like that. And if we want to take a look at our P scale, all we have to do is press D in our viewport, go to geometry, and view these as lit spheres. What that'll do is it'll render each particle in the viewport as a sphere, so we can see what size they are. You can see over here that if I increase my P scale, so let me just multiply this by 2, each sphere gets a lot bigger, right? So that's all that P scale is, and that gets recognized when we're rendering. So when we're outputting particles, just make sure you have a P scale. If you don't, some things will default to a value of 1, and you'll just have massive spheres just populating your scene, and you don't necessarily want that, so just trying to make sure you always have a P-scale attribute. Now over here, you'll also see that I'm deleting everything except velocity and P-scale. That's because we have loads and loads and loads of attributes at this point, right? And I'll explain to you why that's an issue shortly, but just know that I am cleaning off all of those attributes before I'm outputting my simulation. So I'm only keeping the important things, like the scale of the particles and their velocity. So let me just go back to the stage level, and let's just take a look at how we can render this with motion blur. So all we have to do is drop a Karma render setting. So Karma, and this will drop 2 nodes for us. We just plug this into the first input, and over here, if we set our display flag on this, it still won't do anything, but this viewport is now actually using the settings generated by this node, and we can actually see this. If we go to render settings, you'll see that by default, it'll use viewport settings. So if I switch over here, and I take a look, I only have viewport settings as an option. But if I set my display flag over here, and then use the dropdown, you'll see that I actually have access to these /render settings. This also means I can create lots and lots of different render settings and switch between them. So I could have one for like preview, I could have one for final quality render, all of that. The only thing that I have to change on this Karma render settings node is under camera effects. So over here, I have velocity blur. And by default, I'm saying don't use velocity blur. Now velocity blur is just going to take that V attribute and use it for velocity. If I click on my rain over here, just expand the points out, if I take a look at these variables down here, you'll see that I have prim variables, so Primvars, and one of them is called velocities, right? It's a vector 3. So remember, it changes the name from V to velocities, and that's what it uses for velocity blur. If you don't have velocity blur, that won't work. And so all we'll do is just use velocity blur. Now, as you can see, we just have these streaks of rain. So that one that we just had disappeared, but we now have motion blur on all of our rain, and it might be difficult to see. So just press D and change the background to dark. And hopefully now you can see those streaks of rain, right? So all of those are just little raindrops that have motion blur applied to them. Okay, so over here I have the same thing. I just have my rain with some particles that are getting a rain material. and then I want to output it. So you use the USD ROP node. It's just this one over here. And from here, the only thing that you have to change is this render specific range. By default, it'll be render current frame. We just say render specific range 1 to 120. Notice that we're not saving using $F or anything, because this USD file will actually be time dependent. It will know that it needs to save multiple different frames, and so we don't have to do something like $F.USD. That'll generate multiple different USD files. There are situations where you might want that, but we don't actually want that. We just want a single USD file with all of our rain information inside of it. The cases where you do want this $F.USD is for some very specific situations, but also for when your simulation data starts getting a bit bigger. Sometimes you don't want it all in a single USD file, so you can do each frame as a single USD file. And another thing that you may want to do is flush data after each frame. All that does is, instead of calculating everything at once, so evaluating the entire timeline at once, it'll just clear the existing data each time it processes. So that might be useful for when you have a large simulation and it won't fit in RAM, so the entire sequence won't fit in RAM. Then it'll have an issue generating the USD file. So what you can do is you can just say flush data after each frame, and that'll ensure that each and every frame is saved out rather than the entire sequence all at once. So once you've done that, it's really simple to just bring this back in, right? You can just use a reference node, and then you can just go find your rain and bring it back in. Now, this is the only other thing that I want to show you. So I'm going to save this out, and I just want to see what this evaluates as. All right, so we have rain asset, and I'm going to call this one cleaned, and then just save that to disk. So it'll just take a moment to calculate my simulation. But then I'm going to go up over here and remove this attribute delete node, and then just do another one that's not cleaned. So just a regular one, save to disk. Once again, it'll take a moment to load, and let's go find those on disk. Oh, I made a mistake in my naming conventions, but it's fine. I think this still gets the idea across. The one where I deleted all of those extra attributes is 30 megabytes. The one where I didn't is 140 megabytes. So the file is close to 5 times as big when I don't clean off those extra attributes. So if this is going to be a flip simulation where you have gigabytes of data, this is pretty massive. So just keep this in mind. You always want to be cleaning off those extra attributes, right? Just these over here using an attribute delete node. So oftentimes the things that you'll need are just things like V and P scale, as well as maybe like color or something. A lot of the time you don't need that many attributes. Okay, so that's just working with simulations inside of USD. Let's move on to the next part. So now that we know how to work with basic particle simulations, the other type of simulation that you're probably going to be interested in working with is, of course, pyro or volumes, smoke, that kind of thing. So when we're working inside of Solaris and we want to render our volumes out, we can use MaterialX. Now, MaterialX volume shaders are built in a very particular way, and I'm going to be showing you how to do that. So let's go straight into that. All right, in the last part, we looked at simulations. In this part, I want to look at simulations that have volumes. Now, this doesn't just apply to simulations. This also applies to just standard uniform volumetrics. You can use this for things like volumetrics within your scene. So over here, I just have another simulation. This one is super basic. It might be difficult to see once again, so I'm just going to make the background dark. It's just this over here where I've decided to make some smoke come out of the chimney. So I just have this house and the smoke is coming out of the chimney over there, just like that, right? So let's just say that you want to render this. What is the process of doing that? Well, once again, we have our smoke out over here. If I take a look at it, of course, I have a whole bunch of attributes, but these are detail attributes, so they don't actually take up that much space. So I'm not going to worry about them. What I may want to do is remove excess volumes. So I have density and I have velocity, but if I have other things that I'm not particularly interested in, I may want to remove them. Also, I may want to limit my velocity field to where there is density. That's a pretty good practice to do, where you mask out your velocity volume for only where your density exists. Okay, so to take this to the stage level, we can go over to stage, and over here, I'm just SUP importing in that smoke. I'm then applying a material to it. So I'm just SUP importing in my smoke over here. If I switch to a Karma render view, it will render it. However, it won't render it correctly, so what we're going to rather do is do what's in this material library to give it color and all of that. Okay, so what's inside of this material library? Let's take a look. The most basic way of creating a volume shader for MaterialX is this top one over here. You can see I've just labeled it as basic volume, and I'll show you how to do that one. So the issue with using the USD subnet node over here is that this is for surfaces. You can see that we have a surface output and a MaterialX displacement output. Those aren't actually what we want. You can sort of change the way that this works so it's no longer a surface, but we're not going to be doing that. I'm just going to be creating this at this level over here. So I'm just going to use an MTLX volume over here. So that's an MTLX volume and not an MTLX volume material. Over here, I'm just going to call this smoke basic, and you'll see that it has a VDF and an EDF. Now, a VDF is just for density. An EDF is for emission. So if we're looking at VDF, we're looking at things like smoke. If we're looking at EDF, we're looking at things like fire. So this is how you would build up your MaterialX volume. Now, we can go ahead and add things to the VDF, but before we do that, let's just change which material we're using once again. So this one over here is called smoke_basic. So let's just apply that to our smoke. So we'll do /sim smoke volume 0. Okay, so we're now applying that new one. And one thing that we're going to have an issue with, that we're constantly going to have to do, is just restart our render in the viewport. For some reason, it doesn't behave well when we're working with MaterialX volumes. So it just restarts it every now and then, especially if your volume just kind of disappears from your scene. Okay, so we have this smoke basic. The next thing that we need is for absorption and scattering. So we can just do an MTLX anisotropic VDF and plug this into the VDF, right? This still isn't going to do anything, but if we push this up over here, and let's just restart our render, you'll see that we now have the smoke, but it's just blocky, right? It's just these blocks. And these are actually the bounds of our voxels. So this is not actually using our density, it's just using the sort of shape of our smoke and the bounds of our smoke. So it's saying if there's a voxel, fill it with this value. Nowhere is it saying multiply this by density or define this based on density, right? So those values over there need to be defined by density. So all we have to do that is use a geometry property value, right? MTLX geometry property value, the same one that we use for bringing in Primvars. Instead of bringing in a Primvar this time, we're bringing in a density. And so we just switch that to density, and we can plug that into our absorption and our scattering. And let's just restart this over here. As you can see, we have this very fine smoke, but it is now using our density. So this is the basic way of doing it. But we can expand on this, right? So if you were to expand on this, what would that look like? Well, maybe you want to add a multiply, so an MTLX multiply, and plug it into the top and bottom over here, right? By doing that, what we're allowing is finer control. So I'm going to restart this over here. If I push this up, you can see that I'm actually increasing my absorption and scattering. So I'm increasing the amount of absorption and the amount of scattering, resulting in higher density smoke. And these are just multipliers for that density. But what you'll also notice is that these actually come in as vectors. That's because this is actually expecting a color. So what we can do is, instead of just using this, we can also use a constant to define the color, MTLX constant up here. And this MTLX constant will switch to a color, and we can just choose a color. So I'll just choose red over here. And if I plug this into my absorption, you won't notice anything. But then I need to multiply it by the actual density. So I'm multiplying the color by the density. So let's use a multiply node. And again, we want to use an MTLX multiply, not just a regular one. MTLX multiply. And over here, we just plug that into first input, MTLX multiply into second input, and then that should work if we restart our render, right? Now, do note that absorption is extinction based. So all that means is that we're getting rid of the value that we put in here. So instead of it coming through as red, it'll come through as what's opposite to it on the color wheel. So if we put this to blue, then it'll come through as red, right? That's just how absorption works. It's extinction based. So the next thing that we want is to do the same thing for scattering. So we can make another color node and another multiply. And then once again, we're just doing the same thing. We're multiplying that color by the density, plugging it into scattering, and let's just restart this render, just like that, right? Scattering is not extinction based. So whatever you put into scattering, that's the color you'll get. So just keep that in mind. Extinction based for absorption, but just regular for scattering. So scattering can just be set to some color like this, and we can end up with some interesting smoke, right? So that's all we're doing. And all of this is explained down here. You can see that I have the different types of nodes set up, and it's all explained. So if you want to come back here for reference, you can. All right, that brings us to the end of volume rendering. And so it's pretty straightforward, right? To get good looking volumes, all you have to do is bind in that particular density and then use it for all sorts of things. Same thing if you were to use something like emission for your EDF, you would just bring in emission, right? And where is it getting that from? Well, you can take a look over here. Inside of smoke, under volume, we have density and velocity. Once again, it'll also use this velocity to drive motion blur. So these are all things to just keep in mind, but that's how you work with volumes inside of Solaris and with MaterialX. The next thing that we're looking at is this concept of light mixes and snapshots. Now, these are actually two separate concepts, so they're not exactly connected, but they work really well together. So that's why I'm including them in a single part, because they play off of each other in a very interesting way. A light mixer is just a way for us to control all of our lights in our scene from a single node. And snapshots are a way of taking a snapshot of our entire network. So if you picture your Houdini network in the stage level, if we just take a snapshot of that, as well as a render of what that network produces, then we can actually revert to that snapshot at any point. So we can make loads and loads of changes to our network, make snapshots of them as we're going, and then just revert back to an old snapshot. This is the idea of making look dev a lot easier inside of Solaris, because we can have loads of snapshots and we can just jump between them and decide which ones we like after we've already made all of the changes and things. So let's take a look at how to do that inside of Houdini. All right, in this part, we're looking at light mixers and snapshots. So when we're looking at light mixers and snapshots, these are all things that you're going to be using for when you're trying to define the look of your scene. So in this case, I have this house that's being brought in. If I do a Karma render view, you can see that it's just this house geometry with the cake base, and it's got some lights inside, all right? So those lights are kind of bleeding out, and yeah, that's all we have. We then also add an environment light, a right full light, a left rim light, and then we use a light mixer. So I'm just going to show you from this point, right, what we have. This left rim light over here is coming in from the left side of the house. The right full is coming in from over here. And then we just have a camera positioned over here. So I'm going to remove the light mixer for now. And let's just take a look at what we have from the camera view. So if we take a look at this render, okay, so it's a pretty basic render, right? You just have a sort of rim light, a full light, and an environment light. Now, what happens if you want to change these lights and you have, either loads of lights, or in our situation where the actual asset contains lights, how do we affect those lights? Because we actually want to affect the lights that are inside this house, but we don't really have access to them. Now, you may use something like an edit node, but that's not really a very nice way to work. So what we can use is the light mixer. So drop a light mixer after you've added all of your lights, and what it'll do is it'll show you every light in your scene. You can then select multiple lights by clicking and holding Shift, or clicking and holding Control, and you can just select which lights you want to bring in. So you can see that the house has 2 lights inside of it. If I drag these over to the right, I can now affect them over here, right? So it's a single interface for affecting those things. And so I can change their colors to something like blue, right? So if I change both of the interior lights to blue, you'll see that there's that blue tint coming from inside. Let's make that a bit more noticeable. There we go. You can see inside of the house, we now have blue lights. But that's not all we can do. We can also, affect the exposure and everything from here. And what you'll see is that we also have these 2 little red dots. That's just saying that a change has been made to these things. If we want to revert to defaults, you can just right click and say revert to default and revert to default. Okay, so that's one thing. Let's bring in the rest of our lights. So we bring in these over here. We can also adjust exposure. So let's just click on our environment light over here and reduce its exposure. Right, so we don't want much contribution from that. So you can see that that's making our scene a lot darker. And maybe that's what we want. So let's try for maybe a horror type look. Let's add this rim light and make it red. So we're now doing a red rim light over that side. We're now doing a full color over here. That's red as well. And maybe the lights inside the house are going to be this deep orange. Okay, and then again, we can further decrease this value so that we have something like that. So once we've done this with the light mixer, right, and we have all of these changes that have been made, what happens if we want to, save the look of the scene because we maybe like it, but we also want to experiment with something else? Because after we've made a bunch of changes like this, it's going to be difficult to replicate this. So what we can do is over here, where we have our scene graph tree, there's another drop down just above it. So I'm going to minimize the scene graph tree and just click on this right above it. You'll see that I actually have these 3 over here. I'm going to delete them for now so that I can show you what it is. If I click over here where it says snap, it'll create a snapshot. It'll do a quick render, and if I double click on it, it'll show over here, right? So that's one snapshot, and I can rename my snapshot, so this can be something like horror. So this is the horror shot that I just did. Let's say I then decide to move my camera around. So I'm going to move my camera to a new position like this, and then I'm going to make some changes on my light mixer. So I'm going to change the color over here, back to some nice colors like this. And let's make this kind of summary. So I'm going to increase my environment light value. Left and right rim lights are just going to have a nice warm color. And I'm just going to give a bit of a color to my environment light. So just this slight bluish color. Right, and so maybe this is like, I don't know, some sort of fresh looking scene and you want to add that one as well. All you have to do is click snap. I'm just going to rename this one to something like basic. And then once again, I'm going to make some more changes. I'm going to change my camera, come over here, and let's make this like a vaporwave type thing. So we'll make one pink light, one blue light, reduce the environment light, increase this full light, and change the lights inside the house right over there. So maybe this is like vaporwave, right? So we snap again, vaporwave. And then we realize, actually, I really like the horror look. So if I had to go back and do that now, it would be quite challenging. I've made all of these changes, and I've changed my camera a bunch of times, and so if I want to revert back to that, it's a bit of a mission. All I have to do is bottom left, right click on the one that I like. So if I look at these three, I have horror, basic, and vaporwave. All I have to do is right click on this one and say revert network to the snapshot. And what it'll do is every single thing inside of my stage level will be reverted to what it was when I had this one. And that's not dependent on the light mixer in any way. These are two separate concepts, but they work really well together. That's why I included them as one, because the light mixer allows you to make loads and loads of changes, and then you can snapshot your different changes and then switch between them. So back to the vaporwave one, just like that. And this is incredibly powerful because you can actually have various setups, right? You can have different asset setups. You can have incredibly complex changes being saved into a snapshot, and then you can very easily just revert to that snapshot. So that's just how snapshots work. And you can also do things like render them in the background. You can tag them. There's a bunch of different things that you can do. I'm not going to go into the details of it because I think the basic functionality of it is enough to get you started. And this is just an incredibly useful way for working on your scene and working on look dev. In this part, we're just looking at how to actually get your renders going and some of the more advanced render settings. Now, to start with, we're going to be looking at some of our camera settings, how to do depth of field and all of that. We're then going to move on to how to actually render. And we're going to be looking at things like LPE tags, as well as AOVs. Now, LPE tags are just a way of separating the light contributions in your scene out into various render layers. So if we have a rim light and we have a full light, what we can do is instead of rendering that out as a single beauty pass, we can say render this light out as one pass and this light out as another pass. And then we can composite those two together at the end and individually affect each light. So we can separate light contributions out using LPE tags. And so we're also going to be looking at AOVs. And so that, of course, includes crypto mats. So we're going to be looking at how to generate crypto mats using the Karma render node. So let's get straight into that. Right, so in this part, we're using 12_AOV_LPE. And in this one, we're looking at some render settings and camera settings, as well as how to set up LPE tags so that we can render out light passes. Right, so in this file, we're just sublayering in the house and the cake base. We're adding a layout node, which just adds some suites, and then I'm setting the variant on one of them. So basically, we're just kind of setting up a scene. We have some instances over here, some grass instancing, some smarty instancing, and then just two lights and a Karma render settings node. So a couple of things that I want to focus on. Firstly, we're going to look at the camera. So I'm going to set my display flag one above the Karma render settings node on the full light, and then just switch to my Karma viewport and look through camera one. Okay, so after waiting for a moment, you'll get this render going. And this is with Karma CPU. So this is not an XPU render, this is currently a CPU render. Now, with the camera selected, I just want to go over a few camera settings that allow for this kind of look. So the first thing that I want to focus on is just this focal length and horizontal aperture. I'm not going to go into why this is important or how these settings change your render, but I do just want you to know that sometimes when you place a camera at the Solaris level, these two settings kind of just get blown out. I don't know why, but sometimes you'll end up with a focal length of like 5,000, which for anyone who knows anything about photography, that is just not a thing. So we often need to bring it back down into realistic ranges. And you can actually just control and middle mouse on the focal length and horizontal aperture. And what that'll do is reset it to defaults. From there, you can kind of adjust it. So as you can see, 50 is the default over there, and 20.955 is the default for the horizontal aperture. So I'm going to set this back to 20. And the other thing to take note of is this clipping range. So the clipping range, if we increase this, it will clip anything that is less than a meter away, right? So anything that is a meter or less away, it'll be clipped from our scene. So as you can see, we might end up with some weird clipping if we have the set a little bit higher. So let's just see. Right, so you can see how it's cutting out the foreground over here. Now, this is sometimes important in case you have something small that's kind of in front of your camera. Perhaps it's like a leaf or something from a tree, and it's interrupting your camera view. Then you might want this. But in this situation, we actually want a very low clipping range because we don't want the foreground to be cut out. Same thing with the upper end of this. I find that the upper limit hardly ever gives any issues, but do keep in mind that if you are ending up with clipping at around 2000 meters or so, you can adjust this clipping range over here. So that is under the view tab of the actual camera. Next we have sampling, right? Now, as you can see, I have this shallow depth of field in this render, and that shallow depth of field is controlled by your f-stop and focus distance. So by default, your f-stop will be at 0. If I switch this to 0, I'll have no depth of field. You'll see that everything in the foreground is perfectly in focus and everything in the background is perfectly in focus. An f-stop of 0 inside of Solaris means that we actually don't have f-stop. So kind of just ignore f-stop. Now, any value greater than 0 will be used. So if I set this to like some extremely low value, 0.01, you'll see that we end up with extreme shallow depth of field, right? So you can see that anything above 0 is active. So for this scale scene, anything between like 3.2 to like 1.6 is maybe fine, and that will give you some really good shallow depth of field. However, you also need to take into account this focus distance. So as you can see, I currently have it at 0.5. That means that 0.5 units away from the camera is where our focal point is. So make sure you switch to the transform handles for this, and then have your camera selected. And if we press Shift and F, it will add this line. Now it might be difficult to see, so we can press Shift and F again to make it opaque. And this is our focus plane. So we can see that everything that falls exactly on that line is going to be in focus. Anything beyond it or before it will have shallow depth of field applied, and then obviously the further away it gets, the greater it is, the closer it gets, the greater it is. So the closer to the line that everything is, the sharper and more in focus they will get. And to adjust this, we can just press Shift and then click somewhere, and it will shift the plane back to whatever we've clicked on, right? So I can shift it back to that lollipop over there, or I can even bring it to the foreground over here, and that will blow everything beyond these few things in the foreground out of focus. So I press Shift F again to hide that focal plane. You can see that this over here in the foreground is now in focus. So again, Shift F to show your focal plane, and then Shift plus click to select where that focal plane is, as long as you have your camera selected and you have your transform handle selected. So that's for camera settings, right? And we do have some other options. I'm not going to go into them, but you can experiment with all of them. Things like lens shaders are interesting, but they are Karma specific. So I'm not going to be showing you that right now, but I will actually include an extra file that kind of annotates this and explains it. So if you are interested in using a lens shader, you can. All right. So now let's go ahead to our Karma render settings. So before I switch to that, over here under the Karma perspective, you can see that I have render settings. By default, I only have viewport settings. If I set my display flag on the Karma render settings node, then I'll have access to these over here, right? The render settings over there, or my viewport settings. Now it'll start defaulting to the render settings over here. So all of the settings inside of this node are now defining what's being shown in my viewport. And this is interesting because I have things like denoisers, right? So if I take a look at my denoiser over here, I have the NVIDIA Optics denoiser. So that is under image output filters. And what this allows is for denoising of our image, and it'll actually show in our viewport. You can see that things are being cleaned up, and this will be applied when you render to disk. As you can see, I'm ending up with a very smooth looking image, but as this gets more and more samples, you'll start to notice more detail, right? Basically, NVIDIA denoiser is going to do its best to remove all of the noise from the image. The issue is that if your image is still very noisy, it's basically just going to remove detail thinking that it's noise. So as your image gets cleaner and cleaner, the NVIDIA Optics denoiser will do a better job. So as you can see, I'm starting to regain some of the detail inside of this shot. So when you render to disk, it will actually use that. It'll use the Optics denoiser. And another thing that you'll notice is this over here. Currently, it's using the C AOV, right? So that means that the Optics denoiser is running over the C AOV. And I'm just going to pause this render over here and go through the rest of these settings. Now, when we're looking at AOVs, we're looking at extra layers that get rendered for our image. But if I want to add other AOVs, I can go over to the AOVs or render vars tab over here. And down here, I have all of the other render vars that I can add. Now, as you can see over here, I've currently got my beauty pass. The beauty pass is that C that we saw. So I can actually view that. Over here on the right-hand side of my viewport, I have these layers over here. And these are my render outputs. So these are all of the things that are being output by my render. So I've added those three over there, and we'll get to them shortly. But as you can see, it's currently set to C. C just means beauty pass. So this is your entire render not split up in any way. However, you will see that I also have C_env_light and C_full_light. And that's because I've enabled this split per LPE tag. And this split per LPE tag looks at each of the lights in our scene, and then looks at their contribution, and then splits up our beauty pass into the contribution from each of those lights. So if I go to my full light over here, under the Karma tab, right down at the bottom over here, I have this LPE tag. By default, it would be set to do nothing, so it would be disabled. But if you enable it, so say set or create, and then just set it to $OS, $OS will evaluate as the name of the node, right? So it'll evaluate as full light. And this one up here, same thing, right? $OS, it will evaluate as env_light. So we're adding 2 LPE tags, one on each of these lights, and each one of them have the name of the actual light. Now, when we go over here and we say split per LPE tag, what this allows is for our C, or our beauty pass, to be split into the separate light contributions. So if I click on this one, you can see that this is all of the light contributions given by our env light. And if I set this to C_full_light, you can see that this is what the full light's contribution is. Now, again, you'll notice that this is noisy because the optics denoiser only runs on C. It doesn't run on these extra AOVs, right? So if I go over here to my filters, if I were to add the other 2, then it would work, right? I could add those other 2 if I wanted, but I don't actually have them added at this point. And so that's why they come across as noisy. Now, the great thing is we can actually reconstruct our beauty pass using these 2 light contributions. And then we can adjust the contribution from each light when we're compositing. I'm not going to show you how to do that now. If you are interested in doing that, you can check out a beautiful game. That is a Karma rendering series that I did a while back. But towards the end, I go over AOVs and LPE tags in more detail, and I show you how to actually composite with them as well inside of Houdini. So you can check that out. I'll leave a link for that as well. So, okay, great. We can split our beauty pass using LPE tags. And if we wanted, we could even give 2 different lights the same LPE tag, and they'll be included in the same pass. So that's something that you can do. You can also split different things by LPE tags. You can split something like your combined diffuse by an LPE tag. Same thing with pretty much everything else, right? You can set your subsurface scattering over here and then split it by LPE tags. Now, the only other thing that I want to show you over here is down here. So we have these extra render vars, and by default, it shouldn't have anything, right? It won't have anything over here, but if you click this little plus icon, you can then use the drop down and choose exactly what you want. If you scroll all the way down to the bottom, you'll see that we have CryptoMat object and CryptoMat material name. Now, CryptoMats are extremely useful for compositing. They basically just split up either your objects or materials or whatever kind of criteria you give it so that you can select these things. It's almost like a mask per object. So if I take a look at that, you can see that each object in my scene is given a different color. That means that I can mask certain things. So as you can see, all of the gumdrops have this purple color. So let's say I wanted to change all of my gumdrops to green or something. Then I use this CryptoMat as a mask, and then I just apply a hue shift. So I'm adjusting the hue or the color value of these gumdrops using this CryptoMat as a mask. And so I can single things out, right? So again, to use the CryptoMats, all you have to do is go to the extra render vars, and we can just add these render vars at the bottom over here. And again, we have CryptoMat object, but we also have CryptoMat material name. So you can either split them by each unique object or split it by anything that is sharing a material. So if 2 things share a material, they'll be the same color inside of our CryptoMats. Great. The only other thing is just your basic render settings on these nodes. Of course, you have the primary samples over here. And if you increase this, you'll just end up with a higher quality render at the cost of a longer render time. So you can mess around with this and find a sweet spot for the render quality. Over here, we also have the resolution that we can change. And all of these things are just settings, right? So if we were to actually render, then we use this render up over here, and we can either render a frame range or a current frame, and then we would just click render to disk. Alternatively, you can have multiple render settings nodes, and then on the render up, you can actually choose which render settings you would like to use. You can see over here, we only have one, but if we were to add others, we could actually switch between them and choose which one we want to use. We also have this render delegate over here. So I have RenderMan installed on this computer. So I could do a RenderMan render if I wanted to. So you would just change the delegate over here for the output node, and then it would render using that renderer. Now, just a quick look at XPU. If we switch to XPU over here, you'll see that it changes to path traced samples. This again is just your render quality, so you can slide it up and down. But if I go over here and just restart my render using Karma XPU, it will just take a moment, but we'll end up with a much faster render. So this is still going to use the NVIDIA optics denoiser. So this is going to be using your GPU to actually render the scene. So as you can see, it's not real time, but it's really fast, right? As soon as I stop moving in my viewport, everything starts cleaning up, and it's just really nice. You can actually view your scene using XPU, and it loads everything really quickly. And as you can see, everything does still work. Things like our subsurface scattering, our displacement, everything works using XPU, and this is using MaterialX. So if you were using a Vex-based shader, a lot of these things wouldn't work, but because we're using MaterialX with XPU, there aren't any issues. So XPU is an option if you want to be using XPU. If we take a look over here, we do still have our different layers, just like that. So all of that's cool. All right, so that brings us to the end of this part. Again, all of this is annotated in the files if you want to take a look at just a few of these things that I've left in here. And we're going to be moving on to the final part now, and that'll bring us to the end of the series. So I'll see you in the next part. Right, in this file, we have 13_layers.hiplc. Now, this looks a bit funny, just because I like setting up my nodes like this. I don't know why, but if I just press L, it will organize it like this, and we can just see what we have. So what I've done in this file over here is that I've actually shown you how to kind of set up your files so that they are ready for USD export and so that you are conforming them to the correct standards. So this is a decent way to set up your scenes. And I'm just going to go through a couple of things that I have over here. So things like this, where I'm just importing the cake base and the house, those are all pretty self-explanatory and straightforward. However, I then do an extra thing over here. I have a configure layer node. Now, this over here is just this configure layer node. So I've changed the shape and color of it so that you know where they are in the scene. But this is what they look like by default, just this configure layer. Now, I actually have them as the start new layers. So if I click a start new layer, it is actually the same node, the configure layer node, but it has some of these presets predetermined for us, right? So it has the start new layer and do not flatten, all of that. All right, so what is it doing? Well, this over here brings us onto this concept of layers. And I've actually set up my file so that the concept of layers is very apparent, very clear. If we go over here and just expand this up, you can see that we have our scene graph layers over here. Once I place my cake, you'll see that under the root layer, we have this cake over here, and it says that the save control is implicit. Now, when it says implicit, all that means is that when we save this to a USD file, this will be saved implicitly, right? We're not actually telling it where to be saved or how to be saved or anything like that. So Solaris will find its own way to kind of just save this to disk. Now, to understand this better, we can actually go to this configure layer, and you'll see over here that it now says explicit, right? Something's changed. It was once implicit over here. As soon as I go over here, it becomes explicit. And you'll also see that I now have a save path for it. So if we extend the save path out, you'll see that I'm now saving it to this location, right? And this location is defined by what I've set up here, save path, $hip main USD assets scenes layers $os.usd. If I just see what that evaluates to, you can see that it's main geo.usd, the name of this node .usd. Now, this is important because when we save things to disk with USD, we can actually save things as different layers. And this idea becomes more apparent when we start having different layers. So this is just our main geo. So I have a null over here just telling me that this is my main geometry. Then this over here is for my lights. Again, I have another configure layer node. This one is saving to lights.usd. So you can see at the end here, lights.usd. And again, it does the same thing where it goes from implicit, and then I give it a place to actually save to, and then it switches to explicit. Same thing with the cameras. I have two cameras over here. I've set them up, and then I've used the configure layer node, and I've just said save it to this place over here, and it becomes explicit. Now you will see that when I use this merge node over here, I'm actually merging everything in as separate layers. By default, it'll be simple merge, and that's fine as well, but what it'll do is it'll actually save everything as a single layer. We don't want that. We actually want separate layers, so that each one of these things is brought in as its own layer, right? Because we've configured all of our layers, and when we save it to disk, we want those layers separated out. So we set this to separate layers. Now over here, we also have all of our instancing being done. So over here, I have a reference node, and then I explore my variants because this is that entire instancing workflow that I've showed you before. But what you'll notice over here is that if I extend this out, we actually have more than one implicit path being generated. So in that case, when I use my configure layer node over here, I'm telling it to flatten the input stage. So everything that's coming in, flatten it into one layer, and then save that layer out, right? So I'm saving this layer out once again as something just called references.usd. Then I'm doing all of these extra things, and again, I'm making another node over here for my instances, and in this one over here, when I expand it out, you'll see that there's no implicit saves. Basically, we're just trying to avoid implicit saves. We want to make sure that everything that's being saved to disk is going to a very particular location, right? We want to control where everything is being saved. And then when I bring it all together over here, and then save it to disk, you'll see that it says flatten implicit layers. So what this will do is it'll just take any layer that is implicit, and it'll just flatten it into a single layer. everything that's explicit will be saved separately to disk. So all of this stuff seems very abstract at the moment. So let's actually save this to disk and see what it's doing. So we save this to disk, and you'll notice that there's no errors or anything, and I can now show you where this is being saved. So if I go to main and then USD, you can see that I have this 13_layers.scene_out.usda. That's exactly what I'm saving over here. You can see that that's what's being generated over there. And I'm saving it as a USDA so that we can open it up. So let's open it up and see what's inside. As you can see, it's doing something called sublayers. Now, the sublayers over here are just references to different USD files. You can see that it's referencing a USD file called instances.usd, cameras.usd, lights.usd, main.geo.usd, and we can actually go and look at those files. If we go into our assets over here, into scene, and then layers, these are all of the layers that are actually making it up. So as you can see, we have a cameras USD and instances USD, and these are all of the layers that we've been saving. When we make these configure layer nodes and set a place for them to be saved, that's exactly what we're doing. We're saving everything above them into this layer and saving that layer to disk. Then when we make our final file over here, this final file just references these different layers, right? So I just want to show you that even within a single layer, we can have references to other things. So if I go over here to my geometry over here, I'm using these two reference nodes, right? So they're looking at these locations on disk, cakebase.usd and house.usd, and then I save them as a layer, and that becomes a layer of our main file. But we can actually take a look inside of these files as well and see that these over here are also being referenced, right? So these have a reference to the cakebase.usd. The interesting thing about this is that if there's a change made to this cakebase over here, when we load in this thing that we've saved out, it will firstly put together all the layers, then it'll get to this main geo layer, and it'll try to bring this layer in, but that layer will reference a new house asset. So what's so powerful about this is that because everything is referencing everything else, when we bring everything together, we can have different changes having been made to different layers, but they'll all come together to still form our scene perfectly. I can actually load each one of those layers individually. I can use a sublayer node, and I can go over here and I can choose the file that I want. So I'm just going to go to main, USD, and I can choose the main file, and that'll bring in everything. So as you can see, it's exactly the same as what we have over here, right? So everything over here that gets saved out can be brought back in from this file, or alternatively, we can just bring in a single one of those layers. So if you go to scene over here, we have the different layers. So we can bring in just the main geo over here, and we have just that. Or we can bring in just the lights, just like that. Or we can bring in just the instances, like that. So as you can see, each one of these things are getting saved out as a separate layer, and we can actually work with those layers individually. This is also useful if we're working in a big pipeline, where we have somebody working on just the lights, somebody working on just the cameras, somebody working on just the geometry, and then they can save out their own layers, and we can just sublayer it all back together into a master file like this one over here. Right, so this is just a bunch of layers all being brought together to make this final scene. So this is more of a technical understanding, and this is just something to keep in mind when working with USD, is that we do actually save out layers, and by default, all of it's done implicitly, so we sometimes don't even get to see it. But if we want a more refined workflow, then we should be doing things like this, where we have these configure layer nodes, and we save out each layer individually. So that's just something to keep in mind about layering and setting up your scene. As you can see, we have these nice, neat little inputs, and each one does a very specific task. And then we just save it all to disk, and we can load each one of those streams individually. There's loads of control that we end up with when we're working with USD. So that brings us to the end of this part and the end of the series. All right, that brings us to the end of this tutorial series. I hope that this helped you out. And what would be pretty cool is if you decide to maybe take all of these files, build your own scene, do something cool with it, change it in whatever way you want, then go ahead and just share it. So share it on Instagram, and you can tag us at 9_between, and we'll stop by and take a look at your work. Hopefully, if there's enough artworks coming through, we'll put together a bit of a montage or something, and we'll show it on our channel. You can leave your name and any sort of social media handle, if you want, linked to that image, and we'll go ahead and mention you. So that's it for the series. I do hope it helped you, and I hope you decide to stick around and check out all the other cool things that we have on our channel. So I'll see you next time. Bye.